Right now, floating a million miles from Earth in the cold darkness of space, a machine is shattering everything we thought we knew about the universe. The James Webb Space Telescope was built to answer humanity's deepest questions about the cosmos. Instead, it is creating mysteries that defy our most fundamental understanding of reality itself. Galaxies that should not exist, appearing fully formed when the universe was still an infant. Black holes that grew impossibly massive, impossibly fast, violating every timeline we had calculated. An expansion rate for the universe that refuses to make sense no matter how many times we check the measurements. Ancient structures so massive and complex they mock our carefully constructed theories of cosmic evolution. Atmospheres clinging to worlds where they should have been stripped away eons ago. Objects so bizarre that astronomers had to invent entirely new categories to describe them. If you are ready to see how the most powerful telescope ever built is demolishing the comfortable certainties of physics, hit that like button and subscribe to this channel, because what comes next will challenge everything you thought was settled science. We're about to journey into discoveries so strange, so unsettling, that they are forcing scientists to question whether we truly understand the universe at all. The cosmos is not what we thought it was, and the James Webb Space Telescope is showing us just how wrong we have been. When the James Webb Space Telescope launched on Christmas Day 2021, perched atop an Ariane 5 rocket that lifted off from French Guiana, astronomers around the world held their collective breath. This was not just another space telescope. This was a $10 billion bet on the future of astronomy, the culmination of decades of planning, engineering, and international cooperation. The telescope's mirror, composed of 18 hexagonal segments made of beryllium and coated in a microscopically thin layer of pure gold, spans 21 feet across. To put that in perspective, it dwarfs the Hubble Space Telescope's 8-foot mirror by nearly 3 times in diameter and has more than 6 times the light collecting area. This enormous collecting surface, combined with instruments specifically engineered to detect infrared light wavelengths invisible to human eyes, promised to reveal the universe's earliest moments with unprecedented clarity and detail. The scientific community had specific expectations. They anticipated finding small, primitive galaxies in what astronomers call the cosmic dawn, those first few 100 million years after the Big Bang when the universe was emerging from its dark ages. These early galaxies should have been modest affairs, small collections of stars just beginning to coalesce from the primordial hydrogen and helium that filled space. Scientists expected to confirm their models of hierarchical structure formation, the idea that cosmic structure built up gradually over billions of years. Small things merged into bigger things. Dwarf galaxies combined to form larger galaxies. Galaxy groups assembled into clusters. Clusters organized into superclusters. It was a story of slow, patient construction, of matter gradually organizing itself under gravity's steady pull into the cosmic web we observe today. What they found instead has sent shockwaves rippling through the physics community, waves that are still reverberating nearly 3 years later. The discoveries have not just surprised astronomers, they have fundamentally challenged our understanding of how the universe works. The initial images came through in July 2022, and within days astronomers were scrambling to make sense of what they were seeing. The deep field observations, pointing the telescope at small patches of seemingly empty sky for hours to capture the faintest possible light, revealed hundreds upon hundreds of galaxies. Many of these galaxies existed at distances corresponding to less than 500 million years after the Big Bang, precisely the era astronomers wanted to study. This alone was expected and celebrated. What was not expected, what sent cosmologists into emergency meetings and frantic calculations, was how these galaxies looked. They were not the small, faint proto-galaxies that every model predicted. They were massive. They were bright. In some cases, they appeared as evolved and mature as galaxies that had been growing and developing for billions of years. Some of these early galaxies seemed to contain as many stars as our own Milky Way, a galaxy that has had 13.6 billion years to accumulate its stellar population. Yet these cosmic newcomers existed when the universe was barely 3% of its current age, when it should have been impossible for them to have gathered so much matter, fused so much gas into stars, and organized themselves into coherent structures. The numbers simply did not work. Computer simulations, painstakingly constructed based on our best understanding of physics and cosmology, could not reproduce such monsters appearing so quickly. These simulations incorporate the known laws of gravity, the behavior of dark matter, the pressure of radiation, the cooling of gas, the formation of stars, and countless other physical processes. Researchers run them on supercomputers for weeks or months, modelling how the universe evolved from a nearly uniform soup of matter and energy into the structured cosmos we see today. And yet, when they looked at what their simulations produced at the 500 million year mark, they found nothing like what Webb was seeing. The simulated early universe contained small, dim proto-galaxies exactly as theory predicted. Reality, as observed by Webb, showed something completely different. It was as if someone had shown you a photograph of a 6-month-old infant with the muscular physique and development of an Olympic bodybuilder. The timeline did not permit such rapid growth. The physics did not allow it. Yet there it was, staring back at us from billions of light years away, undeniable and impossible. The crisis was immediate and profound. If these observations were correct, and there was little reason to doubt the Webb telescope's exquisite data quality, then something fundamental was wrong with the standard model of cosmology. This model, formerly called lambda cold dark matter, or LCDM for short, incorporates our understanding of dark matter, the invisible substance that makes up most of the matter in the universe. It includes dark energy, the mysterious force causing the universe's expansion to accelerate. It encompasses general relativity, Einstein's theory of gravity that has passed every test thrown at it for more than a century. This framework has successfully explained decades upon decades of astronomical observations. It predicted the detailed pattern of temperature fluctuations in the cosmic microwave background radiation. It explained how galaxies cluster together across cosmic scales. It accounted for the abundances of light elements like hydrogen and helium. It was, in short, the best tested, most successful theory in all of cosmology. But the James Webb Telescope was now presenting evidence that seemed to violate its core predictions about how structure forms in the universe. Some scientists, particularly younger researchers less invested in existing paradigms, began whispering about a paradigm shift, a complete rethinking of how the universe evolved from the Big Bang to the present day. Others, especially senior cosmologists who had spent their careers refining and testing the standard model, defended it vigorously, arguing that there must be explanations within the existing framework that could account for these observations once we understood them properly. The debate intensified with every new observation the telescope delivered, with papers appearing on the Arxiv preprint server at a furious pace, each offering different interpretations and explanations. By late 2022, as more data poured in from the telescope's various instruments and from different regions of the sky, the picture grew even stranger and more troubling. The telescope was not just finding massive galaxies in the early universe, it was finding them in abundance. Scattered across every deep field it observed, everywhere Webb looked, probing different directions in space, there they were. These oversized cosmic teenagers that theory said should not exist were apparently commonplace, not rare exceptions. The sheer number of them compounded the problem exponentially. Finding one or two outliers could be dismissed as rare statistical flukes, cosmic lottery winners that happen to form under exceptionally favourable circumstances. Every large dataset contains outliers after all. But finding dozens, hundreds of them, across independent observations suggested something systematic was happening, something fundamental that the models had completely missed. This was not a small correction to existing theory. This was a wholesale failure to predict a major population of cosmic objects. Cosmologists immediately began running new simulations, tweaking parameters, adjusting assumptions, searching desperately for ways to reconcile theory with observation. Some proposed that star formation in the early universe was far more efficient than anyone had realized, that somehow gas was converting into stars at breakneck speed under conditions we did not fully understand. Perhaps early stars formed more readily, or burned through their fuel faster, or influenced their surroundings in ways that accelerated subsequent generations of star formation. Others suggested that the measurements themselves might be flawed in subtle ways, that these distant objects were not quite what they appeared to be, that there were selection effects or observational biases making them seem more massive than they truly were. Then came the spectroscopic data, and the mystery deepened dramatically, adding new layers of complexity to an already confounding puzzle. Spectroscopy, the technique of splitting light into its component wavelengths to reveal the chemical composition and physical properties of distant objects is one of astronomy's most powerful tools. When astronomers analysed the spectra of these troublingly massive early galaxies, examining the specific wavelengths of light they emitted and absorbed, they found something peculiar that nobody had anticipated. Many of these galaxies were not simply made of stars, as normal galaxies are. They contained actively feeding supermassive black holes at their centres, massive gravitational monsters that were gorging themselves on surrounding gas and dust. These black holes were not sitting quietly at the centres of their galaxies, as the supermassive black hole at the Milky Way's centre does today. They were active galactic nuclei, voraciously consuming matter and pumping out enormous amounts of radiation across the electromagnetic spectrum. The gas swirling around these black holes, heated to millions of degrees by friction and compression, was emitting so much light that it rivaled or even exceeded the combined output of all the galaxy's stars. This extra light made the galaxies hosting these black holes appear brighter than they actually were, and crucially, made them seem to contain far more stellar mass than they truly did. If you estimated a galaxy's mass based on its brightness, assuming all that light came from stars, you would massively overestimate if a significant fraction actually came from a black hole's accretion disk. This discovery offered a potential resolution to the impossible galaxy problem, a way to reconcile observation with theory without completely overthrowing the standard model of cosmology. If much of the light astronomers were seeing from early galaxies came from black holes rather than stars, then the actual stellar mass of these galaxies could be substantially lower, perhaps low enough to bring the observations back into line with theoretical predictions. The galaxies would still be bright and impressive, but not impossibly massive. The crisis might be averted. A team led by Catherine Chorowski, a graduate student at the University of Texas at Austin working under the supervision of Stephen Finkelstein, examined this possibility in exquisite detail. They identified a class of objects in the Webb data that appeared as small red dots, compact sources emitting most of their light at infrared wavelengths with a distinctive red colour. These little red dots, as they came to be called, were scattered throughout the deep field images, far more numerous than anyone expected. Spectroscopic analysis of these objects revealed they harboured rapidly accreting supermassive black holes at their cores. The diagnostic signature was unmistakable. Extremely broad emission lines in their spectra, indicating gas moving at thousands of kilometers per second, velocities only possible in the intense gravitational field very close to a black hole's event horizon. The physics is straightforward but dramatic. As gas spirals inward toward a black hole, it forms an accretion disk, a swirling maelstrom of superheated material. Friction within this disk, caused by gas particles colliding and rubbing against each other as they orbit at different speeds, converts gravitational potential energy into heat. The innermost regions of the disk, closest to the black hole where orbital velocities are highest, reach temperatures of millions of degrees. At these temperatures, matter emits radiation copiously, from radio waves to X-rays. This radiation can be so intense that it outshines the entire galaxy hosting the black hole. In effect, a single object at the galaxy's centre, perhaps no larger than our solar system, produces more light than hundreds of billions of stars spread across tens of thousands of light years. When Chorowski and her colleagues carefully removed these black hole-dominated galaxies from their analysis of early universe mass estimates, the crisis seemed to ease considerably. The remaining early galaxies, stripped of the brightness boost from central black holes, were still somewhat more massive than models comfortably predicted. They remained at the high end of what simulations could plausibly produce, but they no longer violated cosmology in a catastrophic theory-breaking way. The standard model appeared to survive this particular challenge, battered and bruised perhaps, but fundamentally intact. As Stephen Finkelstein put it in the team's published paper, and in subsequent interviews, the bottom line is there is no crisis in terms of the standard model of cosmology. Any theory that has stood the test of time for so long, that has successfully predicted so many diverse observations, requires overwhelming evidence before being discarded outright. And that overwhelming evidence was not present here. The little red dots, these compact black, hole-powered beacons, had provided an escape hatch, a way to explain the observations without demolishing decades of carefully established physics. It was a relief to many in the field who had feared that the telescope's first observations would require them to throw out their textbooks and start from scratch. But this resolution, satisfying as it was in some ways, came with a significant cost. It meant accepting that the early universe was populated by supermassive black holes, far more numerous and far more active than anyone had anticipated. Every model, every simulation, every theoretical prediction had suggested that massive black holes should be rare in the cosmic dawn. They should take billions of years to grow from stellar mass seeds into the supermassive monsters we observe in the present-day universe. Yet here they were, appearing en masse just a few 100 million years after the Big Bang, shining brightly across the infant cosmos. And those black holes, impossible as their sheer numbers were, presented their own profound paradox that may be even more troubling than the galaxy mass problem they helped solve. Supermassive black holes are among the most mysterious and fascinating objects in the entire universe. Nearly every large galaxy astronomers have examined, including our own Milky Way, harbours one of these gravitational monsters at its centre. They're not stellar mass black holes, the kind formed when massive stars explode as supernovae. Those black holes typically mass perhaps 3 to 100 times the mass of our Sun. Supermassive black holes are in an entirely different league. They range from hundreds of thousands to tens of billions of times the mass of the Sun. The black hole at the centre of the Milky Way, called Sagittarius A, masses about 4 million suns. The behemoth at the centre of the galaxy M87, famously photographed by the Event Horizon Telescope, masses about 6.5 billion suns. Some black holes are even larger still, exceeding 10 billion solar masses. These objects grow through well-understood processes that require vast amounts of time. They consume gas and dust from their surroundings, pulling material in through their overwhelming gravitational attraction. They devour stars that wander too close, tearing them apart in tidal forces before swallowing the debris. When galaxies merge, which happens commonly throughout cosmic history, their central black holes eventually spiral together and merge, combining their masses into a single larger black hole. This gradual accumulation of mass, whether through accretion or mergers, takes enormous stretches of time to build up to supermassive status. Billions of years in most cases. The black holes we observe in the local universe have had nearly 14 billion years since the Big Bang to reach their current sizes. That is a lot of time to grow. The James Webb Telescope found supermassive black holes that had no such luxury of time. In observations of galaxies existing just 500 to 600 million years after the Big Bang, when the universe was barely 4% of its current age, astronomers detected black holes with masses equivalent to hundreds of millions of solar masses. Some were even larger, approaching or exceeding 1 billion solar masses. Many of these black holes were actively feeding, their accretion disks blazing so brightly that they qualified as quasars, the most luminous persistent objects in the universe. These objects should not exist so early in cosmic history. The timeline simply does not permit it under any conventional understanding of black hole growth. Consider the challenge in detail. Black holes, in the standard picture, form from the deaths of massive stars. A star must first form from a collapsing cloud of gas, a process that takes several million years as gravity overcomes pressure and the cloud fragments and condenses. The star must then live out its life, fusing hydrogen into helium in its core, and if it is massive enough, progressively fusing heavier and heavier elements up the periodic table. This stellar evolution process takes time. For the most massive stars, the ones that can explode as supernovae and leave behind black holes, this lifetime is relatively short by cosmic standards, perhaps just a few million to tens of millions of years, but it is still time that must be spent. Then the star must explode as a supernova, a catastrophic event that releases more energy in seconds than the Sun will emit in its entire 10 billion year lifetime. If the stellar core that remains after the explosion is massive enough, more than about 3 solar masses, it will collapse into a black hole. This newly formed black hole will have a mass somewhere between 3 and 100 times that of the Sun, depending on the original star's mass and how much material was ejected in the supernova. Now this stellar mass black hole must grow. It can do so through 2 main pathways. First, it can accrete gas from its surroundings, pulling in material from nearby nebulae or from companion stars if it is part of a binary system. Second, it can merge with other black holes when its host galaxy merges with other galaxies. Both processes have physical limits that constrain how quickly growth can occur. Accretion, the primary growth mechanism, is fundamentally limited by radiation pressure, a consequence of basic physics that cannot be easily circumvented. As matter spirals toward a black hole, it does not fall straight in. Conservation of angular momentum forces it into an accretion disk, a flat rotating structure surrounding the black hole. Within this disk, friction between gas particles at different orbital radii converts gravitational potential energy into heat. The inner disk, where orbital velocities are highest and friction is most intense, becomes extraordinarily hot, reaching temperatures of millions or even tens of millions of degrees. At these temperatures, matter radiates copiously. This radiation carries momentum, and when it encounters infalling gas, it pushes outward on it, creating pressure that resists further accretion. There is a theoretical maximum rate at which a black hole can accrete matter before the outward radiation pressure becomes strong enough to blow away the infalling gas entirely, halting further growth. This maximum rate is called the Eddington limit, named after British astrophysicist Arthur Eddington, who first calculated it in the 1920s. A black hole growing at the Eddington limit can roughly double its mass every 40 to 50 million years. This may sound fast, but the mathematics are unforgiving. To grow from a stellar mass black hole of, say, 10 solar masses to a supermassive black hole of 1 billion solar masses requires multiplying the mass by 100 million. Even at maximum Eddington limited growth rates, this would take approximately 800 million to 1 billion years, assuming continuous accretion at the maximum rate with no interruptions. But the universe was only 500 to 600 million years old when Webb observed these supermassive black holes. There literally was not enough time for stellar mass black holes to grow this large through standard accretion, even under the most optimistic assumptions. The numbers do not add up. Something is deeply wrong with our understanding. The Webb telescope initially seemed to make the problem even worse. In November 2024, observations of a particularly extreme black hole designated LID 568 suggested it was feeding at a rate approximately 40 times higher than the Eddington limit. If true, this would represent super Eddington accretion at a rate so extreme it defied conventional physics. Such rapid feeding could in principle explain how supermassive black holes grew so quickly in the early universe. If black holes could violate the Eddington limit by factors of tens or hundreds, if they could gorge themselves on surrounding gas at rates far exceeding what radiation pressure should allow, then perhaps the timeline would work after all. The discovery made headlines worldwide as evidence that black holes could grow far faster than theory predicted, that the early universe was so different from today that the normal rules did not apply. Scientists speculated about unusual accretion geometries, about dense gas clouds that could overcome radiation pressure through sheer mass, about magnetic fields channeling material directly toward black holes, about all sorts of exotic mechanisms that might permit super Eddington growth. However, subsequent analysis by the same research team and by independent groups revealed a complication that deflated these extreme claims. The black hole, LID 568, is surrounded by thick clouds of dust, common in the dense gas-rich environment of early galaxies. This dust absorbs and scatters light from the black hole and its accretion disk, making it harder for that light to escape and reach our telescopes. Crucially, dust extinction affects different wavelengths of light differently, dimming blue and ultraviolet light more severely than red and infrared light. This selective absorption creates the illusion of different physical conditions than actually exist. When researchers carefully accounted for dust extinction in their analysis, correcting the observed brightness for the dimming effect of intervening dust, they found the accretion rate was not as extreme as initially thought. LID 568 was indeed feeding rapidly, growing quickly by ordinary standards. But it was not violating the Eddington limit by a factor of 40. The dust had fooled the instruments and the initial analysis, creating the illusion of impossible behaviour where none actually existed. It was a sobering reminder of how challenging it is to interpret observations of distant dust-shrouded objects accurately. This correction did not solve the underlying problem. It merely removed one particularly extreme outlier from the dataset. Even without invoking impossible super Eddington accretion rates, the early universe was still filled with far more massive black holes than models predicted or could easily explain. The abundance problem remained severe. Dale Kachevsky, an astronomer at Colby College in Maine and a member of one of Webb's early observation programs, was stunned by what the telescope revealed. his team's analysis of Webb observations found an abundance of massive active black holes in the early universe 10 to 100 times greater than expected, based on surveys of quasars in the later universe. This was not a small discrepancy. This was not within the error bars of predictions. This was a wholesale failure of theoretical models to anticipate the ubiquity of these objects. Astronomers had known about a handful of extremely massive early quasars for decades, going back to the Sloan Digital Sky Survey in the early 2000s. Researchers like Xiaohui Fan at the University of Arizona had discovered massive black holes at redshifts exceeding 6, corresponding to times less than 1 billion years after the Big Bang. These discoveries were celebrated as important but were considered rare exceptions, statistical lottery winners that somehow managed to form under exceptionally unusual circumstances. The thinking went that if you surveyed enough of the sky, eventually you would find a few examples of these extreme objects, but they should be rare, precious finds requiring extensive surveys to discover. The Webb telescope revealed this understanding was completely wrong. Massive black holes in the early universe were not rare at all. They were everywhere, scattered throughout every deep field the telescope observed. Wherever astronomers pointed Webb's instruments, there they were, little red dots harbouring supermassive black holes, pumping out enormous luminosities. The quasars discovered by earlier surveys were not exceptionally unusual objects. They were merely the tip of an enormous iceberg, the brightest examples of a vast population. This abundance fundamentally challenges our theories of black hole formation. The standard picture, the one taught in textbooks and incorporated in simulations, assumes that all black holes start small. They begin as the stellar mass remnants of massive stars, objects between a few and a few hundred solar masses. From these modest seeds, they grow gradually over billions of years through the twin processes of accretion and mergers. It is a bottom-up scenario where small things slowly build into bigger things through patient accumulation. But this hierarchical growth model struggles desperately to explain the Webb observations. If all black holes started at stellar masses, there simply was not enough time for them to reach supermassive status by the epoch Webb is observing. The math does not work. The physics does not permit it. This implies that the assumption must be wrong. Not all black holes started small. Some must have been born already massive, or must have grown through mechanisms we do not yet understand. Some theorists are now proposing an alternative that was once relegated to the fringes of cosmology. Perhaps some black holes did not start small at all. Perhaps they were born massive, formed through different processes entirely than stellar collapse. These so-called primordial black holes, objects formed directly from the intense density, fluctuations in the very early universe rather than from dying stars, have been a theoretical possibility for decades. The idea traces back to Stephen Hawking and other physicists in the 1970s. Hawking proposed that black holes could have formed during the chaotic first moments after the Big Bang, when the universe was unimaginably hot and dense. During the first fraction of a second, quantum fluctuations in the primordial fireball could have created regions slightly denser than their surroundings. If these fluctuations were large enough and dense enough, they could have collapsed directly into black holes without ever becoming stars first. These primordial black holes could have a huge range of masses depending on exactly when and how they formed. Some might be microscopic, smaller than atoms. Others might be planetary mass. Still others might be thousands or even millions of solar masses, formed from particularly large fluctuations. The key insight is that if primordial black holes with masses of thousands or millions of suns existed in the early universe, they would provide ready-made seeds that could grow into supermassive black holes far faster than stellar mass seeds ever could. For decades, primordial black holes remained an interesting theoretical curiosity with little observational support. Searches for their signatures proved fruitless. Small primordial black holes should slowly evaporate through Hawking radiation, a quantum mechanical process where black holes leak energy and eventually disappear. Scientists looked for the characteristic radiation signature of evaporating primordial black holes and found nothing. Larger primordial black holes should gravitationally lens background light sources, creating detectable distortions. Again, searchers found no convincing evidence. The hypothesis languished, considered unlikely by most cosmologists. but the Webb telescope's discoveries have breathed new life into primordial black holes. A recent study published in 2025 suggested that even a small population of primordial black holes, making up just a tiny fraction of 1% of the universe's matter content, could seed the formation of supermassive black holes in the densest regions of the early universe. If primordial black holes existed with masses of even 1 million solar masses, they could accrete surrounding gas and grow to hundreds of millions or billions of solar masses over the course of just a few 100 million years. The timeline works, the physics works, and most importantly, the model produces predictions that match what Webb actually observes. The calculations show that primordial black hole seeds would naturally gravitate toward the densest knots of dark matter in the early universe, the regions destined to become the first galaxies. Once there, surrounded by abundant gas, they could accrete efficiently and grow rapidly. Within 500 million years, a primordial black hole seed of 1 million solar masses could plausibly reach several hundred million solar masses, exactly the range Webb is detecting. The model fits the data better than scenarios requiring stellar mass seeds to grow at impossible rates. Another innovative explanation involves a hypothetical variant of dark matter itself. Dark matter, the mysterious substance that makes up roughly 85% of all matter in the universe, is effectively invisible to telescopes. It neither emits nor absorbs light. We know it exists only through its gravitational effects on visible matter and light. The standard cosmological model assumes that dark matter consists of particles that interact with each other only very weakly through gravity. These particles pass through each other like ghosts, barely influencing each other at all. This is why it is called cold dark matter. The particles are moving slowly and interact minimally. But what if this assumption is wrong? What if some fraction of dark matter consists of particles that do interact strongly with each other? Such ultra-self-interacting dark matter would behave very differently than standard cold dark matter. These particles would collide with each other, transferring momentum and energy. They would thermalize, reaching equilibrium temperatures, and most importantly, they could clump together far more efficiently than normal dark matter. Simulations of ultra-self-interacting dark matter show something remarkable. In regions where this type of dark matter is present, it can form extraordinarily dense cores at the centers of dark matter halos. These cores, compressed by the weight of surrounding dark matter and unable to support themselves through any form of pressure, become gravitationally unstable. They collapse catastrophically, forming massive black holes directly without any stars being involved at all. This direct collapse pathway bypasses the entire stellar evolution process. You do not need to wait for stars to form, live, and die. You do not need supernovae. The black holes emerge fully formed from the collapse of dark matter cores, with masses potentially ranging from thousands to millions of solar masses depending on the size and density of the core that collapsed. These massive seeds could then grow through normal accretion and merges into the supermassive black holes Webb observes. The ultra-self-interacting dark matter scenario is speculative, requiring the existence of a new type of dark matter particle that has not been detected in laboratory experiments. But it is consistent with known physics and makes testable predictions that future observations can verify or refute. If this type of dark matter exists, simulations show it can naturally produce the abundance of early supermassive black holes that Webb has discovered. These theoretical explanations, primordial black holes, ultra-self-interacting dark matter, and others being proposed almost monthly in the scientific literature, remain speculative. They are attempts to solve a profound problem using extensions of known physics rather than completely new theories, but they illustrate how the Webb telescope is forcing physicists to seriously consider ideas that were previously on the fringes of mainstream cosmology, hypotheses that were interesting but not taken particularly seriously because there was no compelling observational reason to invoke them. The impossible black holes are not going away. They're real, they're numerous, they're demanding explanations that standard, textbook physics struggles to provide, and they represent just one of multiple ways in which Webb is challenging our understanding of the early universe. The black hole problem is intimately connected to yet another mystery the telescope has revealed. The internal structure and dynamics of early galaxies themselves are nothing like what theory predicted. Galaxies in the nearby, present-day universe are elegant, organized structures that display remarkable order and symmetry. Spiral galaxies like our own Milky Way possess smooth rotating disks where billions of stars orbit the galactic center in orderly fashion, their motion governed by gravity in predictable ways. These disks feature graceful spiral arms, density waves that sweep through the stellar population like ripples on a pond, triggering star formation as they pass. Elliptical galaxies, the other major class of large galaxies, are also orderly in their own way. They contain older stellar populations moving in well-defined orbits, creating smooth distributions of light that fade gradually from bright centers to faint outskirts. Even irregular galaxies, those lacking the clear symmetry of spirals and ellipticals, tend to have coherent internal structures once you examine them carefully. They may not be as photogenic as grand spiral galaxies, but they still display patterns of organization. This cosmic order arises from billions of years of gravitational evolution, during which random motions have been damped, orbital planes have aligned, and matter has settled into stable, minimum energy configurations. It is the natural result of gravity doing its patient work over vast timescales. Astronomers fully expected that early galaxies, those forming in the first billion years after the Big Bang, would be less orderly than their modern descendants. After all, they were still in the process of assembling from smaller fragments. They had not had time to fully settle down and organize themselves. But despite this expectation of some disorder, researchers did not anticipate just how chaotic, how violently turbulent, how utterly messy these primordial systems would turn out to be when Webb finally revealed them in detail. A team led by Lola Dunhave and Sandro Tocella at the University of Cambridge used the Webb telescope's near-infrared camera in a rarely utilized observing mode called grism spectroscopy. This technique allowed them to capture faint light from ionized hydrogen gas in distant galaxies and measure its motion. By studying how this gas moved, they could map the internal dynamics of galaxies, essentially taking their cosmic pulse, measuring their internal motions and activity. They analyzed more than 250 galaxies that existed between 800 million and 1.5 billion years after the Big Bang, a substantial sample that provided robust statistical insights into what early galaxies were like. The results were striking and unambiguous. Most of these early galaxies were not smooth, rotating disks at all. They were not mini versions of the Milky Way, slowly evolving toward their eventual mature forms. Instead, they were clumpy, turbulent systems filled with chaos and violent motion. Gas clouds within these galaxies were puffed up and expanding, moving in all directions rather than settling into orderly circular orbits. Some galaxies showed signs of beginning to settle into ordered rotation, hints of the spiral patterns that would eventually emerge. But the vast majority were still in a state of violent upheaval, their interiors churning like boiling water, driven by intense bursts of star formation and gravitational instabilities that prevented any calm from settling in. This turbulence has profound implications that ripple through our understanding of galaxy formation. In a calm, rotating disk like the Milky Way, gas can cool efficiently and collapse smoothly to form stars at a relatively steady rate. The gas follows predictable orbits, settles into the disk plane, and gradually condenses where density is highest. This produces what astronomers call a star formation main sequence, a roughly constant rate of star formation that can persist for billions of years. But in a turbulent environment, everything changes. Shocks and collisions between gas clouds heat the gas, raising its temperature and pressure. Hot gas is puffed up and difficult to compress. The heating counteracts cooling, making it much harder for gas clouds to collapse and form stars. Turbulent motions also shear apart fragile protostellar clouds before they can collapse. In principle, this turbulence should suppress star formation, reducing it to a trickle compared to calm environments. Yet star formation must have been proceeding extremely rapidly in these early galaxies despite all this turbulence. We know this from their observed brightness. These galaxies are shining brightly in the infrared, indicating copious emission from young hot stars. The ultraviolet and optical light from these stars, redshifted into the infrared by the universe's expansion, is what Webb detects. Bright galaxies mean lots of stars, and lots of stars mean high star formation rates. So there is a paradox. Turbulence should suppress star formation, but observations show vigorous star formation is happening anyway. The resolution to this paradox lies in understanding a different mode of star formation entirely, one that does not occur in present-day galaxies like the Milky Way. Rather than forming stars at a steady, sustained rate spread out over time, these early turbulent galaxies appear to form stars in intense, short-lived bursts. During these bursts, which might last only a few million to tens of millions of years, star formation proceeds at rates far exceeding what the galaxy sustains on average. Then the burst ends, perhaps when supernova explosions from massive stars blow out the gas, or when a central black hole suddenly turns on and heats the surrounding material. Star formation drops precipitously or halts entirely for a period. Then, after perhaps 100 million years, gas cools again, falls back toward the galactic centre, and triggers another burst. This bursty star formation mode had been hinted at by computer simulations for years, but direct observational evidence was lacking until Webb. The telescope's observations confirmed it on a population-wide scale, showing that most early galaxies were caught in various phases of this burst quiescence cycle. Some were in the midst of dramatic starbursts, others were in quiet phases between bursts. A few were just beginning new episodes of intense activity. The diversity Webb observed reflects galaxies at different points in their tumultuous evolutionary cycles. The turbulence and bursty star formation also dramatically affect how astronomers interpret the mass and age of early galaxies, which ties directly back to the impossible early galaxy problem. Consider a galaxy undergoing an intense burst of star formation, forming stars at a rate of hundreds or thousands of solar masses per year. Most of this star formation produces massive stars, giants dozens of times the mass of the Sun. These massive stars are phenomenally bright, each one shining with the luminosity of tens of thousands or even hundreds of thousands of suns. But they're also short-lived, burning through their nuclear fuel in just a few million years before exploding as supernovae. If you observe such a galaxy during its starburst phase, you see tremendous luminosity, the combined light of all those massive young stars blazing away. If you estimate the galaxy's total stellar mass based on this brightness, assuming a typical mix of stellar masses and ages, you will vastly overestimate. Most of the light comes from the most recent burst, from stars that formed in just the last few million years. The galaxy's actual stellar mass, its total inventory of stars accumulated over its entire history, could be much lower than naive brightness-based estimates would suggest. This is another crucial way the Webb observations, once properly interpreted with sophisticated models of stellar populations and star formation histories, may ultimately ease the tension with cosmological models. The galaxies are bright, yes, they are luminous certainly, but perhaps they're not as genuinely massive in terms of total stellar content as they first appeared in those early, shocking observations. The mass estimates are being refined downward as researchers apply better models that account for bursty star formation and the dominance of light from young, massive stars. Yet, this resolution is not entirely satisfying to many cosmologists. It requires accepting that the early universe operated fundamentally differently from the present day in ways we did not fully anticipate. Star formation in primordial galaxies was not a steady trickle modulated by a few factors. It was a series of violent explosions, each consuming vast reservoirs of gas in cosmic instants, leaving galaxies lurching from burst to quiescence and back again. The physical mechanisms driving this behavior remain debated. What triggered these bursts? Why did galaxy self-regulation fail so dramatically, allowing such runaway star formation to occur? Why did galaxies not settle into smooth disks until much later in cosmic history? These fundamental questions remain open, awaiting answers that will require deeper theoretical understanding and more observations. The turbulence also creates significant observational challenges that complicate the interpretation of Webb's data. When gas moves chaotically in all directions, with velocities ranging from stationary to hundreds of kilometers per second in apparently random patterns, it broadens the emission lines that astronomers use to measure velocities and chemical compositions. Spectral lines that would be narrow and sharp in a calm environment become broad and fuzzy when observed in turbulent gas. This line broadening can mimic other physical effects, making it difficult to distinguish between purely turbulent motion and organized outflows driven by supernova feedback or radiation pressure from central black holes or active galactic nuclei. Disentangling these various contributions to line broadening requires careful modeling that accounts for multiple simultaneous effects. It requires additional observations at different wavelengths that probe different physical conditions, and it requires larger samples to perform statistical analyses that can separate systematic effects from random variations. The Webb observations are providing the raw material for this work, but the full analysis will take years as astronomers develop ever more sophisticated models and apply them to the growing dataset. Beyond individual galaxy properties, the Webb telescope has also revealed unexpected large-scale structure and coherence emerging from what should be pure chaos. In observations of the Serpens Nebula, a star-forming region much closer to Earth where stars are being born right now, astronomers using Webb found something remarkable. Approximately 20 protostars, infant stars still in the process of formation, and accreting mass from their surrounding cocoons, all displayed jets aligned within 24 degrees of each other. These jets, narrow beams of gas ejected along the rotation axes of the protostars, were all pointing in nearly the same direction despite the stars being spread across several light-years. This alignment suggests the stars all formed from a single rotating molecular cloud, with the cloud's angular momentum imparting a preferred direction that the individual stars inherited. While this outcome had been predicted theoretically for decades, Webb provided the first direct observation confirming it happens in nature. It demonstrates that even in apparently chaotic star-forming environments, there can be hidden order, coherence on large scales arising from initial conditions. This finding may have implications for understanding star formation in early galaxies as well. If chaotic regions can nonetheless possess underlying structure and preferred orientations, then perhaps early galaxies were not quite as randomly disorganized as their turbulent motions might suggest. Perhaps the strangest structural finding from Webb's early universe observations came not from studying stars or gas, but from examining the overall shapes of young galaxies and what those shapes imply about dark matter. A team led by Álvaro Pozo at the Donostia International Physics Center in Spain, with participation from Arizona State University cosmologist Roger Windhorst, analysed the morphologies of young galaxies in Webb images taken through the JWST Advanced Deep Extragalactic Survey, or JADES for short. What they found was peculiar and potentially revolutionary. Many of these early galaxies appeared elongated, stretched into filamentary structures rather than the compact, roughly round blobs expected for galaxies embedded in standard dark matter halos. According to the conventional cold dark matter paradigm, dark matter clumps hierarchically into relatively spherical or slightly elliptical halos. Galaxies then form at the centres of these halos, collapsing from gas that has fallen into the dark matter gravitational wells. Since dark matter dominates the mass and hence the gravitational potential, galaxies should inherit the shapes of their host halos to some degree. Spherical halos should produce roughly round galaxies, or at least galaxies without strong preferential elongation in any direction. But Webb's observation showed something different. Young galaxies frequently displayed marked elongation, often by factors of 2 or 3 or more, stretched along filaments like beads on a string. Their morphologies looked more like extended filaments than compact ellipsoids. This was unexpected and difficult to explain within the standard cold dark matter framework without invoking special circumstances or unusual viewing angles for large numbers of galaxies simultaneously. The observation aligns intriguingly with theoretical predictions from alternative dark matter models, specifically models where dark matter consists of ultralight particles called axions. Axions were originally proposed in particle physics to solve a different problem entirely, a puzzle about why certain symmetries are conserved in nuclear interactions. But ultralight axions, if they exist, would have profound cosmological consequences. Their quantum properties, specifically the fact that they behave as waves rather than particles on certain scales, would fundamentally alter how structure forms in the early universe. If dark matter consists of particles with masses comparable to electrons or quarks, as in conventional cold dark matter models, then their quantum wavelengths are tiny, far smaller than atoms. They behave essentially as classical particles for all cosmological purposes. But if dark matter particles are 1,000,000 or billion times lighter than electrons, as ultralight axion models propose, their quantum wavelengths become enormous, potentially spanning light years. At these scales, dark matter cannot be treated as discrete particles. It must be treated as a quantum wave field with wave-like properties. One critical consequence of wave dark matter is that it cannot form structure below a characteristic scale set by the particle's quantum wavelength. Quantum pressure resists gravitational collapse on small scales. preventing the formation of compact clumps. This suppresses the formation of small, dense dark matter halos for a significant period after the Big Bang. Instead of producing a hierarchy of clumps on all scales from microscopic to cosmic, wave dark matter favours smooth, extended filamentary distributions. Small-scale clumpiness is erased, only large-scale structure survives. Galaxies forming in such an environment would naturally inherit this filamentary distribution. Rather than condensing into isolated pockets at the centres of compact halos, they would form along extended filaments of dark matter, creating the elongated morphologies Webb observes. The team's simulations showed that wave dark matter models naturally produce galaxy shapes matching the observations without requiring any special assumptions or fine-tuning. The finding is not yet definitive proof that dark matter consists of ultralight axions. Other astrophysical processes might conceivably produce elongated galaxy morphologies through different mechanisms. Primordial magnetic fields, turbulent flows, or anisotropic accretion patterns could potentially stretch galaxies into filamentary shapes under certain conditions. Distinguishing these possibilities requires more detailed observations and more sophisticated models that can make precise, testable predictions, but the result is tantalizing nonetheless. It suggests our understanding of dark matter, one of the fundamental components making up 85% of all matter in the universe, may need substantial revision. The standard cold dark matter model has been extraordinarily successful over the past 4 decades, explaining the rotation curves of galaxies, the clustering of galaxy clusters, the patterns in the cosmic microwave background, and the large-scale distribution of galaxies. It has passed test after test after test, but the Webb observations hint it might be missing something important about how dark matter behaves in the very earliest epochs of cosmic history. If dark matter has wave-like properties that manifest only at the extreme conditions present shortly after the Big Bang, those effects could have left imprints on galaxy formation that persist as observable signatures today. We might be seeing, encoded in the shapes of galaxies 10 billion light-years away, subtle quantum mechanical properties of the particles that comprise most of the matter in the universe. The implications extend beyond galaxy morphology. If dark matter is wave-like, it affects cosmology more broadly. It changes predictions for how galaxies form and evolve. It alters the expected abundance of small satellite galaxies orbiting larger galaxies like the Milky Way. It modifies the expected structure of dark matter halos on various scales. All of these predictions can be tested with future observations from Webb and other telescopes, allowing the hypothesis to be confirmed or refuted through the scientific method. In the research paper published in Nature Astronomy in late 2025, the team dedicated their work to George Smoot, a Nobel Prize-winning cosmologist who passed away shortly after the paper was accepted. Smoot had been among the first scientists to take the ultralight axion interpretation seriously, recognizing its potential to resolve puzzles in cosmology. His willingness to consider unconventional ideas, even when they contradicted mainstream models, exemplified the kind of open-minded but rigorous thinking that drives scientific progress. The Webb discoveries he helped inspire may ultimately vindicate his intellectual courage. These discoveries about galaxy structure, turbulence, and dark matter all connect to perhaps the most profound and most troubling mystery that the Webb telescope has not just revealed, but actively intensified. The expansion rate of the universe itself refuses to make sense no matter how carefully we measure it. For nearly a century since Edwin Hubble's revolutionary observations in 1929, we have known with certainty that the universe is expanding. Space itself is stretching, carrying galaxies away from each other like raisins in an expanding loaf of bread. This expansion is not motion through space, but the expansion of space itself, a consequence of general relativity and the hot Big Bang origin of the universe. Hubble discovered this expansion by measuring the distances to nearby galaxies using Cepheid variable stars and comparing those distances to the galaxies' velocities, measured from the redshift of their spectral lines. He found a direct correlation. More distant galaxies receded faster, exactly as expanding space would predict. The rate of this expansion can be quantified by a number called the Hubble constant, which expresses how far space is stretching as a function of the distance. If you measure the recession velocity of a galaxy at a known distance, you can calculate the Hubble constant. This number is fundamental to cosmology. It tells us the age of the universe by allowing us to calculate backward to when all galaxies were at the same location. It reveals the universe's composition by constraining models of cosmic evolution. It determines the fate of cosmic expansion, whether space will expand forever or eventually recollapse. And it provides a critical test of cosmological models. If our theory of how the universe works is correct, then different methods of measuring the Hubble constant should all yield consistent results. For decades they did, at least within the uncertainties of the measurements. But as observational techniques improved and measurement precision increased, a troubling discrepancy emerged. By the 2010s, this discrepancy had grown from a nagging inconsistency into one of the most significant and perplexing crises in modern physics. The problem is straightforward to state but appears impossible to resolve. Different methods for measuring the Hubble constant give different answers that disagree far beyond any plausible measurement error. There are two primary approaches, each measuring different epochs and using different physics. The first method looks at the cosmic microwave background, the faint radiation filling all of space that is the remnant heat from when the universe was just 380,000 years old. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, a process called recombination. This sudden change allowed photons to travel freely through space, for the first time instead of being constantly absorbed and re-emitted by charged particles. These ancient photons, their wavelengths stretched by cosmic expansion from optical into microwave frequencies, reach us today from every direction in the sky. Satellites like the European Space Agency's Planck mission have mapped the temperature fluctuations in this cosmic microwave background radiation across the entire celestial sphere with extraordinary precision. These tiny temperature variations, typically just a few hundred thousandths of a degree, encode an enormous amount of information about the early universe. The specific pattern of hot and cold spots depends on the density of matter and energy, the amounts of normal matter versus dark energy, the speed of sound in the primordial plasma, and numerous other fundamental parameters. By carefully measuring this pattern and comparing it to theoretical predictions from general relativity and particle physics, cosmologists can infer what the universe was like at that early epoch. They can then use models of cosmic evolution, incorporating everything we know about how matter and energy behave under gravity, to calculate forward in time from that ancient snapshot to the present day. This process yields a predicted value for the current expansion rate, the Hubble constant we should measure today if our cosmological models are correct. The Planck data, combined with other complementary observations, gives a value of approximately 67.4 km per second per megaparsec. This number needs unpacking. A megaparsec is about 3.26 million light-years, a standard distance unit in cosmology. The Hubble constant of 67.4 km per second per megaparsec means that for every 3.26 million light-years of distance you move away from us, the recession velocity caused by expanding space increases by an additional 67.4 km per second. A galaxy 10 megaparsecs away recedes at 674 km per s. A galaxy 100 megaparsecs away recedes at 6,740 km per s, and so on, linearly with distance. The second method for measuring the Hubble constant observes the present-day universe directly using what astronomers call the cosmic distance ladder. This technique builds up distance measurements step by step, starting with nearby stars whose distances can be measured through geometric methods, then extending to more distant objects using various classes of standard candles, objects whose intrinsic brightness is known or can be calibrated. The most important rung of this ladder uses Cepheid variable stars, pulsating stars whose variations in brightness follow a tight relationship with their average luminosity. By measuring a Cepheid's pulsation period, astronomers can determine its absolute brightness. Comparing this to its apparent brightness as seen from Earth then gives the distance through the inverse square law of light. Using Cepheids, astronomers can measure distances to nearby galaxies out to about 100 million light-years. In some of those galaxies, Type Ia supernovae occur, stellar explosions caused by white dwarf stars, reaching a critical mass through accretion and detonating catastrophically. These supernovae have remarkably consistent peak brightness after accounting for their light curve shapes, making them excellent standard candles visible across vast cosmic distances. By observing Type Ia supernovae in galaxies whose distances are known from Cepheids, astronomers can calibrate the supernova absolute brightness. They can then observe supernovae in much more distant galaxies where Cepheids are too faint to detect, measuring distances extending out billions of light years. Combining these distance measurements with recession velocity measurements from redshifts gives the expansion rate directly. This local, direct method, refined over 3 decades by teams led by astronomers including Adam Rees, winner of the 2011 Nobel Prize in Physics for the discovery of cosmic acceleration, consistently produces a higher value for the Hubble constant, approximately 73 kilometers per second per megaparsec, about 8 to 9% higher than the cosmic microwave background prediction. Both measurements are incredibly precise, with formal uncertainties of only 1 or 2%. The measurements have been checked and rechecked using different samples of supernovae, different Cepheid variables in different galaxies, different analysis techniques, different ways of accounting for potential systematic errors. Independent teams using independent datasets get consistent results within each method, yet the two methods disagree at high statistical significance, more than 5 sigma, meaning the probability this is just random chance is less than 1 in a million. This is the Hubble tension, and it represents a fundamental challenge to our understanding of cosmic evolution that refuses to go away no matter how carefully we measure. When the James Webb Space Telescope came online with its unprecedented sensitivity and resolution, one of its highest priority tasks was to cross-check the Hubble Space Telescope's measurements that underpin the local distance ladder. Perhaps there were subtle systematic errors in Hubble's observations that a more capable instrument could identify and correct. Maybe stellar crowding in distant galaxies, where multiple stars blur together in ground-based and even Hubble images, was causing errors in Cepheid brightness measurements. Perhaps dust extinction was being misestimated, making stars appear dimmer than they truly are and inflating distance estimates. There were numerous potential sources of error that needed to be carefully examined. In 2023 and 2024, Webb observed the same Cepheid variable stars that Hubble had studied in 5 galaxies at distances ranging out to 130 million light-years. These galaxies, including NGC 4258, NGC 5468, and others, had each hosted multiple Type Ia supernovae over recent decades, making them critical calibrators for the supernova distance scale. Webb's observations used its superior infrared sensitivity, which penetrates dust better than optical light, and its sharper imaging, which could resolve individual stars that Hubble could not separate. The team, led by Adam Rees, analysed Webb's data with meticulous care, comparing Cepheid by Cepheid with Hubble's measurements. The results were definitive, and for those hoping Webb might resolve the tension, deeply disappointing. Webb confirmed Hubble's measurements with exceptional precision. The Cepheid distances were accurate. Stellar crowding was not a significant issue after all. Webb's superior resolution showed that Hubble had correctly measured the brightness of individual Cepheids in nearly all cases. Dust extinction corrections appeared valid. All the concerns about potential systematic errors were addressed and found to be minimal. As Rees stated in multiple presentations and papers, the team had now spanned the whole range of what Hubble observed and could rule out measurement error as the cause of the Hubble tension with very high confidence, exceeding 8 sigma. Far from resolving the tension, Webb's observations made it worse by confirming it was real. They eliminated the most plausible escape hatches that would have preserved both measurements and the standard cosmological model. With 2 of NASA's flagship space telescopes now in complete agreement about the local expansion rate, and with the cosmic microwave background measurements also rock solid and confirmed by multiple satellite missions, the implication became unavoidable. Either our model of cosmic evolution is incomplete in some fundamental way, or something truly unusual is happening with the universe's expansion that we do not understand. Several explanations have been proposed, each with strengths and weaknesses. One possibility is that dark energy, the mysterious component driving the accelerated expansion discovered in 1998, is not a cosmological constant as the standard model assumes. A cosmological constant means dark energy has exactly the same density everywhere in space and at all times in cosmic history. It is truly constant. But perhaps dark energy actually evolves, varying in strength over cosmic time. If dark energy was weaker in the early universe when the cosmic microwave background formed, and has strengthened over the intervening billions of years, this could explain why local measurements yield a higher expansion rate than early universe predictions. Testing this hypothesis requires observations at intermediate cosmic epochs, probing the expansion history between the cosmic microwave background era 13.8 billion years ago and the present day. The Webb telescope is beginning to provide such data, but results so far have been inconclusive and complicated. Different analyses of intermediate redshift data point in different directions, and the error bars remain large enough that clear conclusions are difficult to draw. Another intriguing explanation invokes new physics operating in the very early universe, before the epoch when the cosmic microwave background formed. Perhaps there was an additional burst of accelerated expansion during the first 100,000 years after the Big Bang, driven by a form of energy called early dark energy. This energy would have influenced how the universe evolved during the cosmic dark ages before recombination, subtly altering the relationship between cosmic microwave background observations and the predicted current expansion rate. The effect could potentially bring the two measurements into alignment by changing what expansion rate we should predict from the cosmic microwave background data while leaving the cosmic microwave background pattern itself essentially unchanged. However, early dark energy introduces substantial new theoretical complications. It requires adding components to the cosmological model with properties carefully tuned to produce the desired effect without violating other observational constraints, and it lacks independent evidence beyond its potential to resolve the Hubble tension. Many cosmologists are skeptical of invoking new physics solely to solve a single problem, especially when that new physics seems ad hoc and tailored specifically to the problem at hand. A third possibility, unsettling to many astronomers because of what it implies about our cosmic perspective, is that we live in an unusual location in the universe. Specifically, we might reside inside a large cosmic void, a region where matter density is lower than the cosmic average. In such an underdense region, the gravitational attraction from denser matter outside the void could add extra velocity to galaxies within it, making the local expansion appear faster than the true cosmic average expansion rate. Observations suggest we do indeed live inside an underdense region called the KBC void, named after its three discoverers. Surveys of galaxy distributions show that within about 1 billion light-years of Earth, galaxy density is roughly 20% lower than cosmic average, a substantial deficit. The size and depth of this void might be sufficient to account for at least part of the Hubble tension, adding several kilometers per second per megaparsec to local expansion rate measurements. This explanation is uncomfortable philosophically because it appears to violate the cosmological principle, a foundational assumption of modern cosmology stating that the universe is homogeneous and isotropic on large scales, that Earth does not occupy any special or unusual location. Finding ourselves near the center of an abnormally large void seems to contradict this principle, suggesting we are indeed in a special location. Throughout the history of science, from Copernicus onward, we have progressively removed Earth from privileged cosmic positions. The void explanation seems to reverse this trend, placing us back in a cosmically unusual location. However, not all researchers agree the tension is real. Interestingly, a competing analysis using Webb data found a different result that muddies the picture further. Wendy Friedman, a distinguished cosmologist at the University of Chicago who has spent her career measuring cosmic distances, led a team that measured the Hubble constant using 3 independent methods based on Webb observations of 10 nearby galaxies. Their methods differed from the SH0ES team's approach, using different types of standard candles including carbon-rich stars and the tips of the red giant branch, classes of stars whose absolute brightness can be calibrated independently of Cepheids. Friedman's team obtained a value of 70 kilometers per second per megaparsec, with uncertainties that overlap both the cosmic microwave background value of 67.4 and the local SH0ES value of 73. Based on this result, they concluded that there may not be strong evidence for a Hubble tension after all. Their measurements suggested the truth might lie somewhere between the two extreme values, consistent with both within the uncertainties. This finding, if confirmed by additional observations, would ease the crisis substantially, suggesting that improved measurements will eventually converge rather than maintaining distinct values. However, the discrepancy between Friedman's result and Rees's result highlights the extraordinary difficulty of making these measurements accurately, even with the most advanced instruments available. The methods use different distance indicators with different systematics. They make different assumptions about stellar populations and dust extinction. They calibrate against different reference galaxies. Small differences in any of these choices can shift the final answer by several percent, enough to change the conclusion substantially. The scientific community remains divided. Some researchers, following Rees's analysis, believe the Hubble tension is a genuine crisis requiring either new physics or a recognition that we live in an unusual cosmic environment. Others, following Friedman's analysis, think improved measurements will eventually show consistency within the standard model. Still others suspect the truth lies somewhere in between, that both groups are correct in some aspects but missing something in others. The debate continues, with new papers appearing almost weekly proposing various solutions or challenging existing measurements. What seems clear is that the Hubble tension is not going away easily. The Webb telescope, rather than resolving it decisively, has transformed it from a nagging inconsistency into a full-blown crisis that demands explanation. Either we are missing something fundamental about how the universe expands, about the nature of dark energy, about the physics of the early universe, or about our location in the cosmic web. None of these options is comfortable, but all of them are scientifically fascinating, opening potential doorways to discoveries that could revolutionize our understanding of cosmology. While cosmologists continue wrestling with these large-scale cosmic mysteries, planetary scientists using the Webb telescope have been uncovering equally bizarre and equally inexplicable phenomena in the atmospheres surrounding distant worlds circling other stars. Exoplanets, worlds orbiting stars other than our Sun, have fundamentally revolutionized our understanding of planetary systems and the diversity of worlds the universe can produce. Since the first confirmed detection of an exoplanet around a Sun-like star in 1995, when Swiss astronomers Michel Mayor and Didier Queloz discovered a Jupiter-mass planet in a 4-day orbit around the star 51 Pegasi, astronomers have discovered more than 6,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. These worlds span an extraordinary range of properties. There are hot Jupiters, gas giants larger than Jupiter but orbiting their stars closer than Mercury orbits the Sun, with surface temperatures exceeding 2,000 degrees Celsius. There are super-Earths and mini-Neptunes, worlds with masses between Earth and Neptune, planet types that do not exist in our solar system. There are ice giants, ocean worlds, lava planets, and probably countless other categories we have not yet imagined. Characterizing the atmospheres of these distant planets represents one of the most challenging and scientifically rewarding frontiers in exoplanet science. It allows us to move beyond merely cataloguing planets' masses and orbits to actually understanding what they are made of, how their climates work, and potentially whether they could harbour life. The James Webb Space Telescope has made atmospheric characterization possible in ways previous instruments, including Hubble, could only dream of. One of Webb's very first major atmospheric discoveries came in observations of the exoplanet WSP-39b, a gas giant located approximately 700 light-years from Earth in the constellation Virgo. WSP-39b is a hot Jupiter, roughly the same size as Jupiter but orbiting its star at just 5% of the distance between Earth and the Sun, completing each orbit in about 4 days. When WSP-39b passes in front of its star, as seen from Earth, the event called a transit, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. Different molecules in the atmosphere absorb starlight at specific characteristic wavelengths, leaving fingerprints in the transmitted light spectrum that reveal the atmospheric composition. Webb's observations of WSP-39b detected carbon dioxide in unprecedented clarity and detail, marking the first definitive unambiguous detection of this molecule in an exoplanet atmosphere. Previous observations had hinted at carbon dioxide, but the detections were marginal, at the edge of detectability. Webb removed all doubt. The observations also found water vapour, sodium, potassium, and most surprisingly, sulfur dioxide, a molecule formed through photochemical reactions driven by intense ultraviolet radiation from the planet's star. The detection of sulfur dioxide was scientifically significant, far beyond just adding another molecule to the list. It demonstrated unequivocally that photochemistry, chemical reactions driven directly by starlight rather than by temperature and pressure alone, is actively shaping exoplanet atmospheres. This had been predicted by theoretical models for decades, but had never been directly observed before. Photochemistry can create molecules that would not form under equilibrium conditions. It can dramatically alter atmospheric composition, creating chemical disequilibrium that serves as a potential biosignature for life if found in a habitable zone rocky planet's atmosphere. Seeing photochemistry at work in WSP-39b's atmosphere opened a new window into understanding how exoplanet atmospheres evolve and respond to their stellar environment. But some of Webb's atmospheric discoveries were far stranger and far more challenging to explain than finding expected molecules doing expected chemistry. In December 2024, researchers announced the strongest evidence yet for a substantial atmosphere on a rocky exoplanet, a world-designated TOI 561b that orbits a star about 280 light-years from Earth. This discovery challenged conventional wisdom about how ultra-hot planets should evolve. TOI 561b is what astronomers classify as an ultra-hot super-Earth. It has a radius roughly 1.4 times Earth's radius, making it larger than Earth but substantially smaller than Neptune. It orbits its host star at a distance less than 1/40th that of Mercury from our Sun, completing each orbit in less than 11 hours. This extraordinarily close proximity places the planet's dayside temperature at approximately 2,400 degrees Celsius, hot enough to melt rock and vaporize many elements. Under such extreme conditions, every theoretical model and every piece of conventional wisdom suggested that any atmosphere should have been stripped away billions of years ago, leaving a bare, airless, rocky surface directly exposed to the fierce stellar radiation. Yet Webb's observations told a completely different story. Using the near-infrared spectrograph instrument, the telescope measured the heat emitted from TOI 561b's dayside during what astronomers call a secondary eclipse, when the planet passes behind its star and we observe only the starlight, allowing us to subtract that background and isolate the planet's thermal emission. The observations covered more than 37 continuous hours and captured 4 complete orbits of the planet around its star, an observational tour de force providing remarkable data quality. Analysis of this thermal emission revealed something unexpected and inexplicable by standard models. The planet's nightside temperature was not as cold as it should be if the planet had no atmosphere at all. Without an atmosphere to transport heat through winds and circulation, the dayside would be blazingly hot, while the nightside would be nearly freezing at perhaps 300 Kelvin or colder, its only warmth coming from internal radioactive decay and residual heat from formation. The temperature difference between day and night should be enormous, exceeding 2,000 degrees. But the observations showed the night side was substantially warmer than this, indicating that heat was being redistributed efficiently from day side to night side. This process requires an atmosphere. Without one, there is no mechanism to transport energy around the planet. The observed night side temperature could only be explained if a substantial atmosphere exists, carrying heat through circulation and moderating the day-night temperature contrast. The team considered several alternative explanations before concluding an atmosphere was necessary. Perhaps a global magma ocean circulating beneath the surface could transport heat, but modelling showed that without an atmosphere the nightside surface would cool and solidify, forming a solid crust that would halt circulation and prevent heat transport. A thin layer of rock vapour, vaporized silicate compounds hovering just above the molten surface, was another possibility. Extremely hot planets can have rock vapour atmospheres where the constituents are normally solid materials like silicon dioxide and magnesium silicate. But calculations showed such a tenuous envelope would provide insufficient heat transport to explain the observations. It would be too thin and too short-lived, evaporating and escaping to space too quickly. The best explanation, the only explanation that fit all the observational constraints, was a thick atmosphere composed of volatile gases likely including carbon dioxide, water vapour, sulfur dioxide and similar molecules. Such an atmosphere could transport heat effectively through global wind patterns, while also shielding the surface from some of the stellar radiation through absorption and scattering. This thick, gaseous envelope could maintain itself in a delicate balance, with volcanic outgassing from the magma ocean below replenishing gases lost to space through various escape processes. This discovery fundamentally challenges prevailing theories about the evolution and fate of close-orbiting rocky planets. It suggests that even under extreme stellar irradiation exceeding anything experienced by planets in our solar system, some planets can retain substantial atmospheres not just for millions of years, but for billions of years, potentially the entire age of their planetary systems. The mechanism protecting the atmosphere remains unclear and hotly debated. Perhaps the planet formed with such enormous quantities of gas that even intense ongoing mass loss has not yet depleted its atmospheric reservoir. Or perhaps, as the team suspects, the atmosphere is being continuously replenished from below, with vigorous volcanism driven by tidal heating and radioactive decay, injecting fresh gases into the atmosphere as fast as or faster than escape processes remove them from the top. Another bizarre and spectacular atmospheric discovery involved an exoplanet with one of the most extreme properties yet measured. WASP 107b, a superpuff planet located approximately 210 light-years from Earth. This planet is almost exactly the same size as Jupiter, with a diameter 94% of the gas giant's, making it one of the largest known exoplanets. Yet its mass is only 12% of Jupiter's mass, giving it an extraordinarily low density, about 1/10 the density of Jupiter and roughly 6 times less dense than styrofoam. It is so fluffy, so bloated with gas relative to its mass, that astronomers classify it as a superpuff, one of the least dense objects ever discovered. WASP 107b orbits its star about 7 times closer than Mercury orbits our Sun, making it very hot with equilibrium temperatures around 750 degrees Celsius. Webb observations in late 2024 revealed dramatic atmospheric phenomena occurring on this bizarre world. Using high-resolution spectroscopy, researchers detected a vast cloud of helium gas extending nearly 5 times the planet's diameter into space, forming an enormous coma surrounding the planet. This helium was being stripped from the planet's outer atmosphere by intense stellar ultraviolet and extreme ultraviolet radiation through a process called photoevaporation, where high-energy photons heat the upper atmosphere to such high temperatures that gas atoms achieve escape velocity and stream away into space. What made the observations truly remarkable was the structure of this escaping atmosphere. The helium cloud was visible not just surrounding the planet, but also distributed both ahead of and behind the planet along its orbit, forming leading and trailing tails like a comet. The leading tail was particularly striking and significant. It indicated that gas was being ripped away from the planet so violently and with such high velocities that the helium was racing ahead of the planet as it moved through space, unable to keep up with the planet's orbital motion. Detailed modelling suggested mass loss rates reaching several 100 billion kilograms per second, an absolutely staggering rate of atmospheric erosion that, if sustained over billions of years, could strip away much of the planet's current mass. The spectroscopic observations also revealed surprising and puzzling chemical signatures. Methane, a molecule that should be abundant in a hydrogen-rich atmosphere at WASP 107b's temperature, according to thermochemical equilibrium models, was conspicuously and mysteriously absent. Methane forms when carbon and hydrogen combine at moderate temperatures in reducing oxygen-poor environments, precisely the conditions expected in a gas giant atmosphere. Its absence suggests something dramatic is happening to destroy methane or prevent it from forming in the first place. The research team proposed that vigorous vertical mixing driven by stellar heating is dredging up gases from deep within the planet's atmosphere, where chemical compositions differ from the cooler upper layers. In the planet's hot interior, high temperatures and possibly ultraviolet radiation photochemically destroy methane, breaking it down into simpler molecules or atomic constituents. This methane-depleted gas is then transported upward by powerful convection and vertical winds, reaching the observable upper atmosphere faster than methane can reform. The absence of methane, combined with detections of water vapor, carbon dioxide, and sulfur dioxide, paints a picture of an atmosphere in violent upheaval. Its chemistry driven far from equilibrium by the extreme energy input from its nearby star. Atmospheric escape, the process stripping WASP 107b's atmosphere, is a critical phenomenon in planetary evolution. Even Earth loses some atmosphere to space every day, roughly 3 kilograms per second, primarily hydrogen atoms that diffuse to the top of the atmosphere and achieve escape velocity. But for Earth, this loss is trivial, insignificant over billions of years. For WASP 107b, the loss rate is orders of magnitude higher, billions of times faster than Earth's trickle. Over the remaining lifetime of WASP 107b's system, potentially billions of years, this planet may shrink substantially, losing much of its puffy, gaseous envelope and transforming into a denser, smaller world. Perhaps becoming a Neptune-like planet or even a super-Earth if mass loss proceeds far enough. Studying this atmospheric erosion in action provides invaluable insights into how planets evolve under extreme stellar irradiation, how they lose primordial atmospheres acquired during formation, and how they transform from one planetary type to another over cosmic time. These observations may help us understand Venus's evolution, Earth's twin planet that lost vast amounts of water over billions of years and transformed from a potentially habitable world into a hellish pressure cooker. They may reveal the fates of many close-orbiting exoplanets that started as mini-Neptunes but gradually eroded into bare, rocky super-Earths. Perhaps Webb's most technically ambitious and scientifically stunning atmospheric study to date came in late 2025, when researchers succeeded in creating the first three-dimensional temperature map of an exoplanet's entire visible atmosphere. The planet studied, WSP-18b, is a massive ultra-hot Jupiter located 400 light-years from Earth. This giant world masses about 10 times Jupiter's mass, and orbits its star every 23 hours at a distance of just 3.5 million kilometers, far closer than Mercury's 58 million kilometer orbit around our Sun. The team, led by researchers at the University of Maryland and Cornell University, applied a technique called spectroscopic eclipse mapping. They observed WSP-18b as it passed behind its star during secondary eclipse, watching how much light at different specific wavelengths disappeared as different regions of the planet's atmosphere were progressively hidden from view. By carefully analysing these variations and how they changed over the course of the eclipse, tracking which parts of the planet were visible at each moment, they could reconstruct a map of temperature variations across the entire dayside hemisphere, visible to Webb. The results revealed extreme temperature contrasts far exceeding anything seen on planets in our solar system. The hottest regions, located near the substellar point where the star appears directly overhead, reach temperatures exceeding 3,000 degrees Celsius, hot enough to vaporize iron and other metals and destroy water molecules, breaking them down into constituent hydrogen and oxygen atoms. Cooler regions, still scorching by any Earth standard but relatively cooler compared to the hottest zones, retained intact molecular water. Temperatures in these cooler areas were perhaps 2,400 to 2,600 degrees Celsius, a mere few hundred degrees cooler, but enough to allow water molecules to survive. This temperature variation across a single planet's atmosphere had been predicted by sophisticated three-dimensional atmospheric circulation models, but it had never been directly observed before. Seeing it actually happening on another world, measuring where molecules survive intact and where they are thermally destroyed, validates those models while also revealing details they had not predicted. The three-dimensional map also showed evidence of powerful winds transporting heat from the star-facing dayside toward the night side, creating complex circulation patterns with jet streams and temperature gradients that drive weather systems utterly alien to anything on Earth. Creating this map required extraordinary observational precision and complex data analysis. The team had to disentangle subtle wavelength-dependent variations in eclipse depth, changes of just a few parts per million in the overall brightness, from noise, systematic errors, instrumental effects, and stellar variability. The fact they succeeded demonstrates Webb's exceptional stability and sensitivity, while also showcasing the sophisticated analysis techniques astronomers have developed. These atmospheric studies collectively demonstrate the Webb telescope's transformative power for planetary science. They reveal that planetary atmospheres exhibit far more diversity and complexity than simple models suggested. Some planets defy expectations by retaining atmospheres they should have lost eons ago. Others are caught mid-transformation, their atmospheres being stripped away in real time as we watch. The chemical compositions span from familiar molecules to exotic species produced by photochemistry. Temperature structures range from uniform to wildly variable. Each new observation brings surprises that force refinements and expansions of our theoretical frameworks. Yet even these strange and unexpected exoplanets, as bizarre as their properties may be, are not the most perplexing objects the Webb telescope has discovered. That dubious distinction belongs to an entirely new class of cosmic objects that astronomers are still struggling to understand and classify nearly 3 years after their discovery. When astronomers began the painstaking work of sorting through and cataloguing the first deep field images returned by the James Webb Telescope in mid to late 2022, examining each detected source to classify its nature and properties, they noticed something peculiar that had no precedent in previous surveys. Scattered liberally throughout these deep exposures, mixed in among the thousands of distant galaxies, were numerous tiny red points, compact sources emitting most of their light at infrared wavelengths longer than 2 microns with a distinctive red colour that made them stand out from ordinary galaxies. These little red dots, as they came to be informally but universally called, appeared with remarkable and unexpected frequency across every field Webb observed. There were far more of them than models of distant galaxy populations predicted, suggesting the telescope had stumbled upon an entirely new population of cosmic objects that Hubble and ground-based telescopes had been unable to detect. Initial photometric analysis, examining the sources in multiple filters to measure their colours and estimate their properties, suggested these objects were very distant, existing at high redshifts corresponding to times less than 1 billion years after the Big Bang, precisely the epoch astronomers were most eager to study. Their red colour could be explained 2 ways. They could be extremely dusty, with dust grains in the galaxies or their surroundings, absorbing shorter wavelength blue and optical light, and leaving only longer wavelength infrared light to escape, giving them their red appearance. Alternatively, they could be dominated by old stellar populations, red and yellow giant stars that naturally emit primarily at red and infrared wavelengths. Both scenarios were plausible, but something about these little red dots did not fit either explanation perfectly. They were too bright and too compact for their apparent sizes. Their spectral energy distributions, the way their brightness varied with wavelength, had unusual shapes that did not match templates of normal galaxies at any redshift. Most perplexingly, there were simply too many of them. Population synthesis models, which predict how many galaxies of different types should exist at different redshifts based on our understanding of galaxy formation and evolution, consistently underestimated the number of little red dots by substantial factors. It was as if the models were missing an entire population. Speculation ran wild in the astronomical community about what these objects might represent. Were they extremely dusty starburst galaxies forming stars at prodigious rates, but hidden behind thick veils of dust? Were they ancient, massive galaxies that formed remarkably early and were now coasting along, dominated by old stellar populations? Were they some exotic new class of object never before seen? Each hypothesis had adherents and detractors, but conclusive answers required spectra that would reveal the object's compositions, physical conditions, and kinematics. Obtaining spectra of these faint, compact sources was technically challenging but scientifically essential. Spectra split light into its component wavelengths, revealing emission and absorption lines from specific atoms and molecules that serve as unmistakable fingerprints of composition and physics. Between January and December 2024, an ambitious observing program called RUBIES, an acronym for Red Unknowns, Bright Infrared Extragalactic Survey, used nearly 60 hours of precious Webb observing time, spread across multiple observing epochs, to collect spectra for a statistical sample of 4,500 distant galaxies spanning a range of colours, brightness, and morphologies. Within this large sample, they identified and obtained high-quality spectra for 35 little red dots. When the spectra came back and researchers examined them for the first time, the results were utterly astonishing and immediately controversial. The spectra showed extremely broad emission lines, far broader than expected for normal star-forming galaxies at similar redshifts. These broad lines indicated gas moving at velocities of thousands of kilometers per second, velocities only possible in environments with extraordinarily strong gravitational fields. Such extreme velocities are the characteristic signature of gas swirling in the powerful, gravitational grip very close to a supermassive black hole's event horizon, orbiting at substantial fractions of the speed of light in the innermost regions of an accretion disk. The little red dots were not ordinary galaxies dominated by stars. They were active galactic nuclei, systems harbouring supermassive black holes actively accreting matter from their surroundings and releasing enormous amounts of energy across the electromagnetic spectrum. But the characteristics and properties of these particular active galactic nuclei were unlike any previously observed in decades of studying these objects with previous generations of telescopes. Standard active galactic nuclei, the kind detected by earlier X-ray optical and radio surveys, display characteristic spectral signatures that are well understood. There are broad lines from the accretion disk, narrow lines from more distant clouds, continuum emission from the disk itself, and often signs of jets and outflows. The little red dots showed some of these features, but with unusual relative strengths, odd shapes, and peculiar additional components that did not fit standard templates. Most strikingly, many showed what is called a Balmer break, a sudden decrease in brightness at a specific wavelength around 365 nanometers, though redshifted into the infrared due to cosmic expansion, caused by hydrogen atoms absorbing ultraviolet photons. Balmer breaks are common in galaxy spectra. They typically indicate the presence of many stars on the main sequence, particularly A-type stars with surface temperatures around 10,000 Kelvin. The strength of the Balmer break correlates with the stellar population. More A stars means a stronger break, but theoretical calculations show there are limits to how strong this feature can be in a galaxy dominated by normal stellar populations. The break depth cannot exceed certain values set by stellar physics and population synthesis. One object in particular, designated with the informal nickname the Cliff, due to the dramatic appearance of its spectrum, displayed a Balmer break so pronounced, so extreme, that it exceeded by factors of several what any realistic stellar population could produce. The break was deeper than should be possible if the light came from stars. It resembled the spectrum you would see from a single very hot star more than from an entire galaxy containing billions of stars of all different types. This should not be possible. A single star cannot outshine an entire galaxy, yet the spectrum seemed to demand exactly that. Faced with this conundrum, the researchers were forced to consider radically new interpretations. The team, led by Anna de Graaf at the Max Planck Institute for Astronomy, proposed a revolutionary new model they termed a black hole star, a name chosen to emphasize the object's hybrid nature, combining properties of stellar and black hole-powered emission. In this theoretical picture, the central supermassive black hole and its brilliantly glowing accretion disk are completely enshrouded, hidden within a thick cocoon of dense neutral hydrogen gas. This hydrogen envelope is so thick and so dense that it absorbs virtually all the high-energy ultraviolet and X-ray radiation from the inner accretion disk, preventing it from escaping directly. Instead, the absorbed energy heats the hydrogen gas to temperatures of tens of thousands of Kelvin. At these temperatures, hydrogen atoms are partially ionized and re-emit the energy they absorbed, but in a different form, producing a spectrum dominated by hydrogen emission lines and a characteristic continuum shape. Crucially, the specific geometry and physics of this re-emission process can produce an extremely strong Balmer break far stronger than stellar populations could generate, because you're essentially seeing the emission from a single continuous surface of hot gas, rather than from many discrete stars with different temperatures. The black hole star model, while speculative and requiring specific geometric configurations that may be rare or unstable, successfully explained the Cliff's peculiar spectrum and the spectra of other little red dots showing similar extreme properties. If correct, this interpretation has profound implications reaching far beyond just classifying some unusual objects. It suggests that the growth of supermassive black holes in the early universe occurred in a hidden phase, a period where the black holes were buried deep within dense cocoons of gas that obscured them from view at optical and ultraviolet wavelengths, making them invisible to previous generations of surveys. Only in the infrared, where the Webb telescope operates, do these obscured growing black holes reveal themselves. The infrared light can penetrate the surrounding dust and gas more easily than shorter wavelengths. This could explain why earlier surveys dramatically underestimated the number of active supermassive black holes in the early universe. They were there all along, growing rapidly and releasing enormous energy, but hidden behind veils of gas and dust that made them invisible to optical and UV-sensitive telescopes like Hubble. This interpretation also connects directly back to the impossible early galaxy and impossible black hole problems. If many of the bright, apparently massive galaxies detected in Webb's first observations are actually little red dots, compact active galactic nuclei rather than extended star-forming galaxies, then their luminosity comes primarily from black holes rather than from integrated stellar populations. This substantially reduces estimates of stellar mass in the early universe, easing the tension with cosmological models that struggle to explain how so much mass could have assembled so quickly. But it simultaneously intensifies the black hole growth problem by revealing that supermassive black holes were even more numerous and more active in the early universe than anyone suspected. Not only do we have the black holes discovered as bright quasars in earlier surveys, we now also have this vast population of obscured black holes revealed by Webb. Together, they represent a staggering abundance of massive black holes existing when the universe was less than 1 billion years old. Not all researchers are convinced by the black hole star interpretation. The model requires very specific viewing geometries, with our line of sight passing through the dense hydrogen envelope at just the right angle to produce the observed spectral signatures. It requires particular density structures and temperature gradients in the gas that may be difficult to achieve or unstable against collapse or evaporation. Alternative explanations involving different combinations of stellar populations, dust extinction geometries, and black hole activity might also fit the data if the models are sufficiently complex and parameterized. Distinguishing between these competing interpretations will require additional observations, gathering data at wavelengths the current spectra do not cover, obtaining higher spectral resolution that can resolve narrower features, and observing larger samples to determine whether the extreme properties are truly common or represent rare outliers. These observations are planned and in some cases already underway, with results expected over the next few years. Regardless of the final interpretation of little red dots, which will surely evolve as more data accumulate and models improve, they represent a population of objects that existing theories did not predict. They are yet another example of how the Webb telescope is revealing an early universe far stranger and more complex than our models anticipated. Every deep field reveals more mysteries. Every spectrum brings surprises. The cosmos is refusing to cooperate with our neat theoretical frameworks. As these diverse Webb discoveries accumulate across multiple areas of astrophysics, galaxy evolution, black hole growth, atmospheric composition, and more, a pattern emerges. The universe's earliest epochs were more violent, more active, more extreme, and more richly structured than standard models comfortably allow. Star formation proceeded in explosive bursts rather than steady streams. Black holes grew faster than conventional physics easily permits, or appeared already massive from new formation pathways. Galaxies churned turbulently for hundreds of millions of years before settling into orderly rotation. Dark matter may have wave-like properties that suppress small-scale structure. The expansion rate measured locally exceeds predictions from the early universe, and exotic hybrid objects populate the cosmos in numbers and varieties we never anticipated. The James Webb Space Telescope is not breaking physics in the literal sense of discovering phenomena that violate fundamental natural laws like conservation of energy or causality. The laws of physics as we understand them, gravity, thermodynamics, electromagnetism, quantum mechanics, remain intact. Galaxies still form from collapsing gas clouds under gravity's pull. Stars still fuse hydrogen into helium through nuclear reactions. Black holes still curve spacetime according to Einstein's equations. Light still travels at exactly 299,792,458 meters per second in vacuum. These bedrock principles of physics have not been overturned. What Webb is breaking is something different but perhaps equally fundamental. Our models, our theoretical frameworks, our cosmological narratives about how the universe evolved from the Big Bang to the present day. It is forcing physicists and astronomers to confront the uncomfortable possibility that the story we have been telling ourselves about cosmic evolution, while remarkably successful in explaining many observations, is incomplete or fundamentally wrong in important ways that we did not anticipate and still do not fully understand. This distinction matters. Breaking a physical law would require overthrowing centuries of established science, discarding theoretical frameworks that have passed countless experimental tests. It would be revolutionary in the most dramatic sense. What Webb is actually doing is more subtle but still profound. It is showing that the implementations of physical laws we have been using to model cosmic evolution, the specific scenarios and parameter choices and assumptions we have been employing, do not accurately capture what actually happened in the universe's history. This is how science progresses. Theories are not eternal truths handed down from on high. They are provisional frameworks, our best current understanding of how nature works, useful until observations reveal their limitations. The lambda cold dark matter cosmological model has worked spectacularly, breathtakingly well for more than 3 decades. It has successfully explained the cosmic microwave background temperature fluctuations with stunning precision, Fitting hundreds of data points with a model containing just 6 free parameters, it predicted the acceleration of cosmic expansion before it was observed. It explained the abundance of light elements like hydrogen, helium, and lithium synthesized in the first minutes after the Big Bang. It accounted for the large-scale clustering of galaxies across billions of light years. Test after test after test, the model passed. But now it faces challenges on multiple independent fronts, each one individually concerning but collectively suggesting something more systemic may be wrong. Early galaxies appear substantially more massive and more evolved than simulations can comfortably produce. Black holes exist in numbers and sizes that timeline calculations say are impossible. The expansion rate measured locally disagrees with predictions from the early universe. Galaxy morphology suggests dark matter may have wave properties. Atmospheric retention on ultra-hot planets defies conventional wisdom about atmospheric escape. Little red dots reveal a hidden population of obscured black holes that models did not predict. Not all of these challenges will necessarily survive deeper scrutiny. Some may be resolved through better understanding of observation systematics, through improved models that incorporate previously neglected physics, through reinterpretation of what the data actually show. The history of astronomy is littered with apparent crises that ultimately dissolved when observers got better measurements, or theorists refined their models. The spiral nebulae crisis of the early 20th century seemed to show objects with impossible sizes until Hubble proved they were distant galaxies. Quasars initially appeared to violate energy conservation until we understood they were powered by supermassive black holes. The solar neutrino problem suggested our understanding of nuclear physics or stellar interiors was wrong until neutrino oscillations solved it, but it seems unlikely that all of Webb's challenges will disappear this way. Too many independent observations from different instruments using different techniques point towards similar conclusions. The telescope is seeing real phenomena that demand explanation. Some modifications to our theoretical framework seem inevitable. Several paths forward are being actively explored by researchers worldwide. One possibility is that the basic physics is correct, but our implementations need refinement. Perhaps star formation in the early universe proceeded through different pathways than today, with higher efficiency or different initial mass functions, favouring more massive stars. Perhaps black holes did form from massive seeds, primordial black holes or direct collapse objects, rather than exclusively from stellar remnants. Perhaps the Hubble tension reflects our location in a cosmic void or subtle systematics in one or both measurement approaches. These explanations preserve Lambda CDM's core framework while adding complexity, nuance, and new physical processes to account for observations. Another path involves modifying dark sector physics. Dark matter comprises 27% of cosmic energy density and dark energy, 68%, yet we know almost nothing about either component beyond their gravitational effects. Dark matter might consist of multiple particle species with different properties, including ultralight axions that behave as waves. Dark energy might evolve over time rather than remaining constant, perhaps strengthening gradually or fluctuating stochastically. Either modification would cascade through cosmic evolution, changing predictions for structure formation, expansion history, and galaxy properties. Testing these alternatives requires precision observations that are only now becoming possible with facilities like Webb. A third, more radical path questions whether gravity itself behaves as general relativity predicts on cosmological scales. Modified gravity theories have been proposed for decades, initially to explain galaxy rotation curves without dark matter, later extended to cosmology. While most variants struggled to match observational constraints, some newer formulations make predictions aligned with Webb's findings. If gravitational strength varies with environment or scale, structure could form more efficiently in the early universe, naturally producing larger galaxies and deeper voids. Testing modified gravity requires measuring how matter responds to gravity in different contexts. Galaxy interiors versus intergalactic space, early universe versus late times, high density versus low density regions. The truth may involve combinations of all these factors. The universe is enormously complex. Multiple effects surely contribute to what we observe. Disentangling them demands more data, better models, careful hypothesis testing, and the intellectual humility to follow evidence wherever it leads, even when it contradicts comfortable assumptions. What is absolutely clear is that we are living through a period of profound discovery and fundamental questioning in cosmology. The last time the field faced comparable upheaval was the 1960s, when quasars, pulsars, cosmic microwave background radiation, and X-ray astronomy revolutionized our understanding essentially simultaneously. Those discoveries ultimately led to the standard cosmological model that is now being challenged. The Webb observations may similarly lead to a new synthesis, a deeper theoretical framework that explains both the old successes and resolves the new puzzles. For scientists, this is simultaneously exhilarating and unsettling. The boundaries of knowledge are being pushed aggressively in multiple directions at once. Long-held assumptions face serious questioning. New ideas emerge constantly, some promising, others less so, all requiring careful vetting through observation and theory. The process is messy with conflicting results, heated debates, premature conclusions, and inevitable dead ends. This is science at its most raw and honest, revealing the real process of discovery behind the polished certainty of textbooks. For everyone else, these discoveries offer a profound reminder of how much remains unknown and perhaps unknowable given current tools and understanding. The universe is not a solved puzzle with only minor details left to fill in. It remains deeply, fundamentally mysterious, populated by phenomena that challenge our best efforts to understand them. The James Webb Space Telescope is not just showing us more of the universe in higher resolution. It is showing us how much more there is to learn, how much our current knowledge is provisional and incomplete. Each answer spawns new questions. Each mystery solved reveals deeper enigmas beneath. The telescope continues its observations, returning data at a prodigious rate that will take decades to fully analyze even as new observations accumulate. The science is just beginning. The James Webb Space Telescope's mission is far from over. Launched in late 2021 and achieving full operational status in mid-2022, the observatory was designed to operate for a minimum of 10 years with a goal of 20 years if all systems remain healthy and consumables last. Every year, astronomers from around the world submit hundreds of proposals requesting observing time, far more proposals than the telescope can possibly accommodate. A rigorous peer review process selects the most scientifically compelling proposals, ensuring Webb focuses on questions that matter most to advancing our understanding of the cosmos. Future observations will systematically target and extend the mysteries Webb has already uncovered, attempting to determine whether initial discoveries represent rare flukes or robust populations, whether surprising findings survive deeper scrutiny, and whether emerging patterns point towards specific solutions or demand entirely new paradigms. More galaxies from the cosmic dawn will be studied in exhaustive detail with multi-wavelength photometry and spectroscopy revealing ages, chemical compositions, star formation histories, and internal dynamics. These data will directly test whether early galaxies are genuinely as massive as they first appeared, or whether refined models accounting for black hole emission, bursty star formation, and extreme stellar populations reduce mass estimates to levels cosmological models can accommodate. Observations of little red dots will expand dramatically as researchers seek larger statistical samples that can pin down the prevalence and properties of these enigmatic objects. Higher spectral resolution spectroscopy will resolve narrower features that can distinguish between competing theoretical models. Observations at additional wavelengths, particularly in the mid-infrared red where Webb has unique capabilities, will probe the dust and gas enshrouding these objects, determining whether black hole stars are the correct interpretation or whether alternative models better explain the data. The ultimate goal is transforming little red dots from mysterious anomalies into a well-understood population with clear connections to other galaxy populations and evolutionary pathways. The Hubble tension will be probed through new measurements spanning different distance scales, attempting to map cosmic expansion history between the early universe epoch probed by cosmic microwave background and the present-day measurements from Cepheids and supernovae. By carefully measuring distances and expansion rates at intermediate redshifts spanning a few billion years ago, astronomers can potentially determine whether expansion accelerated recently as dark energy strengthened, remained steady as a cosmological constant would require, or varied in more complex ways. These observations are technically challenging since they require extraordinarily precise photometry and spectroscopy of very faint objects. But Webb sensitivity makes them possible for the first time. Exoplanet atmospheric characterization will advance on all fronts. Webb will observe more rocky planets in or near their stars' habitable zones, where temperatures permit liquid water on the surface. While finding definitive biosignatures like oxygen and methane simultaneously in an Earth-like atmosphere remains beyond even Webb's capabilities, detecting any atmosphere at all on a truly Earth-sized rocky planet would be groundbreaking. We have never detected atmospheres on planets smaller than super-Earths. Even characterizing atmospheres on super-Earths at habitable zone distances remains extremely difficult, since these faint planets yield tiny signals when they transit their stars. For gas giants, Webb will continue mapping three-dimensional atmospheric structures across samples of planets spanning different temperatures, masses, compositions, and orbital distances. By studying how circulation patterns, day-night temperature contrasts, and chemical disequilibrium vary systematically with these properties, astronomers can test atmospheric models, constrain interior structures, and determine how planets form and evolve. Webb will study atmospheric escape from hot Jupiters and super-Earths in detail, documenting how planets lose their atmospheres and potentially transform from one type to another over billions of years. The search for biosignature gases remains a holy grail of exoplanet science, though one that will require significant observational luck or next-generation facilities beyond Webb. Methane and oxygen simultaneously present in an atmosphere with water vapor would be compelling evidence for biological processes, since abiotic chemistry cannot maintain both gases together for geologically long periods. Dimethyl sulfide, produced primarily by marine phytoplankton on Earth, would be an even stronger biosignature since we know almost no abiotic production pathways. But detecting these molecules at the spectroscopic precisions required will be incredibly challenging. Webb has the sensitivity needed, but candidates must be bright enough to yield sufficient signal. This likely requires transiting planets around cool M-dwarf stars, where the planet-to-star size ratio is favourable and stellar variability does not overwhelm planetary signals. Webb will be joined and complemented by other observatories launching this decade that will provide synergistic capabilities for addressing the questions Webb has raised. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will have a mirror similar in size to Hubble's, but with a field of view 100 times larger, allowing it to survey vast regions of sky rapidly. Roman will discover billions of galaxies across cosmic time and measure their properties statistically, providing population-level context for Webb's detailed studies of individual objects. For exoplanets, Roman will use gravitational microlensing to discover thousands of planets at Jupiter-like and even Earth-like masses, orbiting at temperate distances from their stars, planetary populations nearly impossible to detect through other methods. The European Space Agency's Euclid mission, already launched and operational since 2023, is mapping the three-dimensional distribution of galaxies and dark matter across the universe with unprecedented precision, measuring shapes and positions of billions of galaxies to determine how dark matter clusters and how cosmic expansion evolved. These measurements directly constrain dark energy properties and test alternative gravity theories. Combined with Webb's deep characterization of early galaxies, Euclid's wide-area surveys will reveal whether early massive galaxies are common or rare. Clustered or distributed, evolving rapidly or remaining stable. On the ground, enormous new telescopes are under construction that will complement Webb's infrared vision with capabilities at optical and near-infrared wavelengths. The extremely large telescope being built by the European Southern Observatory in Chile will have a segmented primary mirror 39 meters across when completed in the late 2020s, nearly twice Webb's collecting area and 4 times its diameter. Its adaptive optics systems will deliver images as sharp as or sharper than Webb's, despite observing from the ground by correcting atmospheric turbulence in real time. The Giant Magellan Telescope and 30-meter telescope, also under construction, will join the ELT as the world's largest optical telescopes, capable of studying individual stars in distant galaxies and characterizing exoplanet atmospheres with unprecedented precision. The Vera Rubin Observatory, also in Chile, will conduct the Legacy Survey of Space and Time, photographing the entire visible sky every few nights for 10 years starting in the mid-2020s. This survey will discover millions of transient events like supernovae, detect thousands of asteroids and comets, map the distribution of dark matter through gravitational lensing, and catalogue billions of galaxies. The statistical power of this dataset will be enormous, providing population-level constraints on galaxy evolution, structure formation, and cosmology that will contextualize Webb's detailed individual observations. The combination of Webb's depth and sensitivity with wide-field survey's statistical power will be transformative. Webb can study individual objects in extraordinary detail, resolving internal structure, measuring precise compositions and kinematics, and detecting the faintest sources. Surveys provide the big picture of how those objects fit into the broader cosmic context, determining whether Webb's discoveries are common or rare, typical or unusual, representative or outliers. By comparing deep, focused observations with broad, shallow surveys, astronomers can test whether their theoretical models correctly predict population distributions and evolutionary pathways. Theoretical work proceeds in parallel with observations, equally critical for progress. Cosmologists worldwide are already running new generations of simulations incorporating more sophisticated physics to see whether models can match Webb's observations. These simulations now include radiation transfer, magnetic fields, turbulence, chemical evolution, black hole feedback, cosmic rays, and other processes that were previously neglected or treated crudely due to computational limitations. Modern supercomputers and improved algorithms allow much more realistic modeling of galaxy formation, star formation, black hole growth, and large-scale structure development. Different research groups are testing different assumptions about dark matter microphysics, dark energy evolution, inflation models, early universe initial conditions, and gravity modifications. They run simulations forward from the Big Bang to the present day, predicting what the universe should look like at various epochs. Comparing these predictions with Webb observations tests whether particular theoretical frameworks can explain what we actually see. Theories that fail these tests can be ruled out or constrained. Theories that succeed gain credibility and motivate further testing. One exciting possibility is that Webb will discover something completely unexpected, a phenomenon that fits into no current theoretical framework and demands entirely new physics to explain. This has happened repeatedly in astronomy's history. Cosmic acceleration's discovery in 1998 through supernova observations was completely unanticipated, forcing cosmologists to invent dark energy and fundamentally rethinking cosmology's future. Fast radio burst discovery in 2007, brief intense pulses of radio waves from distant galaxies lasting just milliseconds, came as a total surprise and remains only partially explained despite decades of effort. Gravitational waves direct detection in 2015, while long predicted, opened an entirely new window on violent cosmic events like merging black holes and neutron stars. Webb operates at observation's frontier, probing regimes of distance, time, and faintness never before accessible. Frontiers are where surprises happen. The telescope's design capabilities were carefully optimized to address specific science questions, but its actual observations are limited only by astronomers' imagination and the universe's willingness to cooperate. Unexpected discoveries often come from programs designed for different purposes, from serendipitous detections in images taken for unrelated reasons, from peculiar objects that do not fit any predicted category. The telescope's technological limits are well understood and constrain what it can discover. Webb's infrared sensitivity allows seeing the earliest galaxies redshifted into infrared wavelengths and peering through dust clouds opaque to optical light, but it cannot observe in ultraviolet or X-ray wavelengths, where other crucial astrophysical processes occur. Its field of view is relatively narrow, roughly the size of a grain of sand held at arm's length, requiring many separate pointings to map large areas and making blind surveys inefficient. Its location at the second Lagrange point, gravitationally stable but 1 million miles from Earth, means it cannot be serviced by astronauts if systems fail or instruments need repair. These constraints shape what Webb can discover and how quickly science advances. Despite limitations, the telescope has already exceeded expectations dramatically. Its images are sharper than pre-launch predictions because mirror alignment and thermal stability perform better than required specifications. Its instruments are more sensitive than design requirements specified, allowing detection of sources even fainter than planned. The science return has been extraordinary, with major discoveries announced at a pace that has surprised even the mission's planners and advocates. As astronomers gain operational experience and develop new analysis techniques optimized for Webb's unique capabilities, the science will only improve and accelerate. The ultimate question hanging over the field is whether Webb's discoveries will lead to a genuine paradigm shift in cosmology, a fundamental change in how we conceptualize cosmic evolution, or whether they will be accommodated within existing frameworks through incremental modifications and refinements. Scientific revolutions are rare. Paradigm shifts are even rarer. History suggests the latter outcome is more probable since good theories do not collapse easily under the weight of a few anomalies. More often, theories survive by expanding to include new phenomena, by adding complexity and nuance, by accommodating surprises within broadened frameworks. Yet the possibility of revolution cannot be dismissed. If dark matter truly has wave properties fundamentally different from cold dark matter paradigm, if dark energy evolves in ways incompatible with cosmological constant, if gravity deviates from general relativity on cosmic scales, if primordial black holes dominate early structure formation, any of these would constitute revolutionary changes reshaping cosmology's theoretical foundations. The Webb observations provide tantalizing hints that one or more might be necessary. Only time, more data, and careful analysis will reveal whether these hints develop into compelling evidence or dissolve into artifacts and misinterpretations. Either way, the telescope ensures the next decade will rank among the most scientifically productive and intellectually exciting in astronomy's history. If these discoveries have left you questioning everything you thought you knew about the universe, about the reliability of our cosmological models, about the certainty of scientific knowledge, then you are not alone. Professional astronomers around the world are grappling with exactly the same questions, engaged in the same debates, wrestling with the same mysteries that Webb has revealed. The cosmos has proven itself to be far stranger, far more complex, far more resistant to our attempts to understand it than we imagined even just a few years ago before this telescope began its observations. The journey to comprehend the universe will span generations, perhaps centuries, but each step forward brings revelations that fundamentally transform how we see reality, how we understand our place in the grand cosmic story, how we conceptualize the very nature of existence itself. If you want to continue following these unfolding mysteries as Webb returns more data and astronomers refine their theories, hit that subscribe button below and turn on notifications so you never miss an update when new discoveries emerge. These are genuinely historic times in astronomy and cosmology. We are witnessing the universe reveal itself in ways that challenge and inspire, that humble and excite, that force us to confront the limits of our knowledge while simultaneously expanding those limits in unexpected directions. And if you found this deep exploration of the universe's deepest puzzles fascinating, thought-provoking, or mind-bending, give this video a like to help others discover it and join this conversation about what Webb is teaching us. The universe is breaking physics right before our eyes, demolishing comfortable certainties, creating puzzles that will occupy scientists for decades to come. And the James Webb Space Telescope is our guide and witness to this unfolding revolution in understanding. The story is far from over. In fact, we are still in the opening chapters. The next discoveries, the next challenges to theory, the next paradigm-shifting observations could come next month, next year, anytime Webb turns its golden mirror toward a new target and captures photons that began their journey billions of years ago. What those photons will reveal, what mysteries they will deepen or resolve, what assumptions they will confirm or overturn, nobody can predict with certainty. That uncertainty, that openness to genuine discovery, that willingness to follow evidence even when it contradicts cherished theories, lies at the heart of science's power and beauty. We thought we understood cosmic evolution. The universe is showing us how much we still have to learn, and that is exactly as it should be. The James Webb Space Telescope represents humanity's latest and most powerful tool for exploring the cosmos, but it is just one tool in an ever-expanding arsenal. The questions it has raised will drive astronomical research for decades, inspiring new instruments, new theoretical frameworks, new ways of thinking about cosmic evolution. Graduate students today who are analysing Webb's data will become the senior scientists of tomorrow, carrying forward the mysteries and hopefully some solutions. Their students will inherit questions we cannot even formulate yet, problems that will emerge from observations not yet made. This is the essence of scientific progress, each generation building on previous work, extending knowledge incrementally while occasionally making revolutionary leaps, always pushing against the boundaries of ignorance, always seeking to understand more fully this magnificent universe we inhabit. The Webb telescope reminds us that we're still near the beginning of this journey, not approaching its end. The universe holds secrets we have barely begun to glimpse. And that should fill us not with despair at our ignorance, but with wonder at how much remains to discover, how many adventures await, how many paradigm-shattering revelations the cosmos still holds in reserve. Thank you for joining this exploration of how the James Webb Space Telescope is rewriting physics and cosmology. The story continues with each new observation, each new analysis, each new insight into the nature of reality. Stay curious, keep questioning, and never stop wondering about the universe and our place within it. The telescope itself, this remarkable machine floating in the darkness beyond the moon, represents not just technological achievement but human aspiration made manifest. Thousands of engineers, scientists, technicians, and support staff from multiple nations devoted careers to making Webb possible. They solved unprecedented technical challenges, from deploying a tennis court-sized sunshield in zero gravity to aligning 18 mirror segments to nanometer precision while operating at temperatures just above absolute zero. They created instruments so sensitive they could detect the heat signature of a bumblebee at the distance of the moon. They developed data analysis pipelines capable of processing terabytes of observations and extracting meaningful signals from noise. This achievement required international cooperation on a scale rarely seen in human endeavours. NASA, the European Space Agency, and the Canadian Space Agency partnered to fund, build, and operate Webb, pooling resources and expertise from their respective nations. Scientists from dozens of countries contribute to the scientific programs, analysing data and publishing results that advance humanity's collective knowledge, regardless of nationality or borders. In an era often characterised by division and conflict, Webb stands as an example of what humans can accomplish when we work together toward common goals driven by curiosity and the desire to understand. The observations Webb returns belong to all humanity, not to any single nation or institution. After proprietary periods allowing discovery teams first access to their data, all Webb observations become publicly available through archive systems accessible to anyone with internet connectivity. Amateur astronomers have already made discoveries in archived Webb data. Citizen scientists contribute to classification efforts and data analysis. Students worldwide use Webb observations in classroom projects. The knowledge Webb generates spreads globally, enriching education, inspiring young people to pursue science careers, and advancing human understanding of our cosmic context. This democratization of astronomical data represents a relatively recent development in science's history. For centuries, access to the best telescopes and most important observations was restricted to elite institutions and privileged individuals. The development of digital data archives and internet connectivity transformed this dynamic, making frontier astronomical data accessible to anyone with the interest and skills to analyze it. Webb continues and amplifies this trend, ensuring that discoveries made with a $10 billion instrument funded by taxpayers benefit not just the scientists who propose the observations, but the entire global community. The societal impacts of Webb's discoveries extend beyond the immediate scientific findings. By revealing the universe's true nature, by demonstrating how much remains unknown, by showing that our current understanding is provisional and incomplete, Webb reminds us of the value of intellectual humility. In a world where confidence and certainty are often prized above doubt and questioning, where social media amplifies extreme positions and discourages nuance, the Webb telescope models a different approach. Science proceeds by proposing hypotheses, testing them against observation, refining or discarding them based on evidence, and remaining always open to revision when new data emerges. This method, frustratingly slow and uncertain though it sometimes appears, remains humanity's most reliable path to genuine knowledge about the natural world. The telescope also reminds us of deep time's profound reality, of the unimaginable scales on which the universe operates. When we see a galaxy in a Webb image located 13 billion light-years away, we are not merely seeing something far away in space. We are looking backward in time, seeing that galaxy as it existed 13 billion years ago when the universe was young. The light captured in Webb's detectors began its journey toward Earth, when the universe was barely 5% of its current age, travelling across expanding space for longer than Earth has existed, longer than our Sun has existed, longer than the Milky Way has had its current spiral structure. This light is a message from the deep past, carrying information about conditions and processes from an epoch so remote it challenges comprehension. Yet this remoteness makes the connection all the more profound. The atoms in our bodies, the carbon and oxygen and nitrogen and iron, were forged in stars that lived and died billions of years ago. Some of those atoms may have been created in the very early universe Webb observes, formed in the first generation of stars, scattered into space by supernovae, incorporated into subsequent generations of stars and planets, eventually finding their way into the solar system, Earth, and us. We are, quite literally, made of star stuff, as Carl Sagan memorably phrased it. Webb's observations of the early universe are observations of our own cosmic origins, revealing the processes that created the elements and structures that ultimately made our existence possible. This realization places human existence in cosmic context that is simultaneously humbling and inspiring. We are tiny, ephemeral, confined to a single planet orbiting an ordinary star in an ordinary galaxy in a universe containing hundreds of billions of galaxies. Our entire species' existence spans merely hundreds of thousands of years, a cosmic eye blink compared to the universe's 13 billion year history. Every human civilization, every empire, every achievement and catastrophe of recorded history, all of it has occurred in the most recent thousandth of 1% of cosmic time. Yet despite this insignificance on cosmic scales, we've developed the capacity to understand the universe, to trace its history from the Big Bang to the present, to predict its future evolution, to comprehend physical laws operating on scales from subatomic to cosmic. We have built instruments that can detect photons from the edge of the observable universe and decrypt the information they carry about distant eras and environments. We've used mathematics and physics to reconstruct what the universe was like when it was a fraction of a second old, long before stars or galaxies or planets existed. This is remarkable, perhaps miraculous in its improbability. The Webb telescope extends this capacity for understanding, pushing the boundaries of what we can observe and comprehend. It is showing us phenomena we did not anticipate, challenging theories we thought were secure, opening new questions faster than we can answer old ones. This is uncomfortable for those who prefer certainty and closure, but it is exactly what frontier science should do. Telescopes like Webb are built not to confirm what we think we know, but to reveal what we do not know, to break paradigms rather than reinforce them, to show us where our understanding fails so we can build better theories. The coming years will bring more surprises, more challenges, more revisions to cosmology as Webb continues operating and returning data. Some mysteries it has revealed will be solved, others will deepen. Entirely new puzzles will emerge that we cannot currently imagine. This is the nature of exploration at knowledge's frontier. We cannot predict what we will find because if we could predict it accurately, there would be no point in looking. The universe has repeatedly demonstrated its capacity to surprise us, to behave in ways we did not expect, to contain phenomena our theories did not anticipate. Embracing this uncertainty, remaining open to surprise, following evidence wherever it leads even when it contradicts comfortable assumptions. These are the attitudes and practices that have made science successful as a method for understanding nature. The Webb telescope embodies these principles, designed to observe without preconception, to measure without bias, to reveal reality as it is rather than as we expect or wish it to be. The data it returns sometimes confirms predictions, sometimes overturns them, always advances knowledge by replacing speculation with measurement. As we conclude this exploration of how Webb is breaking physics, remember that breaking here means refining, improving, extending, correcting, not destroying. The laws of physics endure. What changes is our understanding of how those laws operate under extreme conditions, our knowledge of what the universe actually contains, our models of how cosmic structures form and evolve. This is progress, moving from less accurate descriptions to more accurate ones, from less complete theories to more complete ones. Always approaching but never quite reaching perfect understanding. The universe is vast beyond comprehension, ancient beyond imagination, complex beyond our current ability to fully model. We have been studying it seriously for mere centuries, with truly powerful instruments for only decades. The Webb telescope represents our best effort yet to probe its secrets, but it is not the end of the road. Future instruments will surpass Webb's capabilities just as Webb surpasses Hubble's. The questions will continue, the mysteries will persist, the journey of discovery will go on. And that, ultimately, is cause for celebration rather than frustration. A universe fully understood would be a universe fully exhausted, holding no more surprises, offering no more opportunities for discovery. The Webb telescope assures us we inhabit no such universe. The cosmos remains strange and wonderful, full of phenomena that challenge and inspire, populated by objects and processes we're only beginning to understand. There will always be more to learn, more to discover, more to wonder about. The adventure continues.